and I will be presiding over this technical conference. With me this morning are Chairman William M. Brawley, Commissioners Tommy Tucker, Don Vandervaart, and John W. Gaida. On November 20th, 2025, Duke Energy Progress, LLC, and Duke Energy Carolinas, LLC, hereinafter collectively referred to at times as Duke, filed general rate case applications that included applications for performance-based regulation, hereinafter referred to at times as PBR applications, pursuant to North Carolina General Statute 62-133.16 and Commission Rule R1-17B. Pursuant to North Carolina General Statute 62-133.16, subsection J3, and Rule R1-17B, subsection C, Commission is required to schedule a technical conference regarding projected transmission and distribution projects to be included in the PBR applications within 90 days after the filing of PBR applications. Additionally, electric utilities are required under Rule R1-17B, subsection C2, to make a filing regarding the projected transmission and distribution projects no later than 5 days prior to the first session of the technical conference. The original filing was filed on January 20th, 2026, and updated documents were filed with the Commission on March 5th, 2026. On December 16th, 2025, the Commission issued an order in both dockets scheduling a technical conference for January 27th, 2026. The January 27th technical conference was postponed due to Winter Storm Firm and rescheduled to occur on this date and time. The December 16th order requested parties to file a petition to intervene and a notice of intent to participate in the technical conference, and required those participants to file a list of individuals who will appear at the technical conference by January 16th, 2026. The order also noted that the Commission may ask questions of Duke or any other party, but parties are not permitted to cross-examine one another. However, it appears that no intervening parties have opted to participate in today's technical conference. Duke has indicated that its presentation today will proceed in 4 parts. After each presenter, we will pause to take questions from the Commission. We plan to break this afternoon for lunch approximately 12:30, subject to change depending on where we are in the proceedings. Before we proceed, I would like to extend sincere gratitude on behalf of the Commission to line workers, vegetation crews, and other contractors who worked under extreme difficult and dangerous conditions during Winter Storm Firm. We also recognize the critical role of the system operators in the energy control centers who maintain grid stability throughout the event. Their professionalism, dedication, and commitment to the customers they serve are deeply appreciated. With that, we are ready to begin, and I'll recognize the attorneys for Duke. You could identify yourselves for purposes of the record, and then we'll proceed with the appropriate presentations.
Thank you, Presiding Commissioner McKissick, Chair Brawley, members of the Commission. My name is Melissa New. I'm with the law firm of Troutman Pepper Lott. I'm here today on behalf of Duke Energy Carolinas, LLC, and Duke Energy Progress, LLC. And with me is my colleague, Josh Combs, who was previously admitted pro hoc vice by order of this Commission on January 9th, 2026.
Thank you. Would you like to go ahead now and present the panelists that are before us?
Yes. Here to your right is Mr. Brent Guyton. He is the Director of Power Grid Operations and Asset Management. Sitting next to him is Mr. Bennett Bogg, General Manager of Transmission Engineering. And then next to him is Mr. Sam Holman, Vice President of Grid Integration and Strategy. And standing is Mr. Gray Thompson, who is Director of Energy Storage Development. Thank you.
Very good. Well, they can go ahead and proceed. I know we have a schedule before us, which indicates that they will likely take approximately 1 hour for their presentation. Is that consistent with what your understandings are?
Approximately 2 hours.
For this particular panel?
Yes, sir.
Okay. All right. Well, let's go ahead and proceed. We might push that projected time frame for lunch back a little bit, but we want to make sure we make it through what they have to share with us. Thank you.
All right. Good morning, commissioners, and thank you to all the attendees who have joined the technical conference today. As we know, your time is valuable, and we believe you will find today's session informative. My name is Brent Guyton. I am the Director of Distribution Asset Management for Duke Energy here in the Carolinas. For today's technical conference, as Ms. New noted, we have 4 subject matter experts who will be speaking on the distribution, transmission, grid planning and integration, and storage investments identified in the MYRP. I will be our first speaker, followed by Bennett Fogg, then Sam Holman, and finally Gray Thompson will wrap up our presentation. We will spend the next couple of hours sharing information on the discrete and identifiable distribution, transmission, grid planning and integration, and storage investments identified by DEC and DEP's MYRP2. While separate topics and parts of the grid, they are all part of the integrated grid here in North Carolina. While each of us will be very focused on describing specific parts on the different parts of the grid, they are all physically connected and collectively together provide benefits to our customers here in North Carolina.
Now, one point of clarification. After your presentation dealing with the distribution projects, we will have questions at that time about distributions.
Absolutely.
And we'll do that for each subsequent section, just for purposes of clarity.
Absolutely. Thank you.
Thank you.
Over the course of the technical conference, we will provide an overview of the evolving landscape of the North Carolina electric grid and the trends that drive our system planning. We will also share an overview of the distribution, transmission, grid planning and integration, and reliability microgrid projects and programs that are included in our MYRP2 proposal and which were identified in the pre-technical conference materials. We will talk about how the MYRP2 investments build on and extend the capabilities initiated in MYRP1 and are necessary for the company to both maintain and advance the grid. In addition, we will also provide specific examples of the planned work identified during the second multi-year rate plan period. It is important to note that this presentation today is an overview of the previously submitted materials documenting the scope of our MYRP, and it is not intended to provide detail on every program or project identified. As a reminder, on January 20th, 2026, Duke Energy provided the following information. Detailed description for each planned improvement program or project, and that description included the purpose and description of the work to be completed, a summary of the expected benefits, the estimated installation costs for the planned distribution, transmission, grid integration, and storage work. Additionally, Duke Energy has provided a complete list of the planned projects, including projected in-service dates, estimated total cost for each individual project, House Bill 951 policy considerations addressed, and lastly, cost-benefit analyses that list the cost and benefits for each program or project, and most include a financially based CBA. There were MYRP supplemental filings on DEC on February 12th and on DEP on February 26th. These included updated project estimates, amended per NCUC Rule R1-17B subsection F. For DEC specifically, the supplemental updated 169 of the 577 project locations, resulting in a net decrease of 19.6 million, or approximately 0.72% of the total cost. The DEP supplemental updated 184 of the 498 project locations. This resulted in a net decrease for DEP of $42 million, or approximately 1.63% of the total cost. These supplemental updates are reflected in our presentation today. Shown is a list of the top drivers shaping our proposed grid improvements. First, storm hardening to avoid outages and reduce restoration times. The last 6 years have yielded the fourth in 2023, the third in 2021, and the most active in 2020 Atlantic hurricane seasons in history. The number and severity of these events have not slowed down since the first T&D MYRP Tech Conference in 2022. Hurricanes and storms since the last rate case include Helene and Debbie in 2024, which caused extensive damage to DEC's and DEP's system across the Carolinas. DEC and DEP assets will continue to be impacted by severe weather events, including hurricanes, flooding, as well as winter storms. We must continue to undertake efforts to strengthen the electric grid to make it more resistant to these threats, while also making our system more resilient to recover faster when outages do occur. Technology investments, including automated restoration capabilities. We leveraged advances in distribution automation technology to start on self-healing teams in the 2010s timeframe that have led to multi-millions of hours saved or avoided in customer outage durations. The self-optimizing grid, or SOG or SOG, takes the self-healing technology to the next level through advanced circuit segmentation and automated control system upgrades. Strengthening the grid against physical and cyber threats. Physical security of our substations. It has been 3 years now since the Moore County substation shooting. Since that time, we have completed comprehensive surveys of hundreds of substations and critical infrastructure across our 6-state service area. This survey has helped to drive improvements that include monitoring, physical, and cyber protection. Wildfires, such as we experienced this past spring in the Carolinas, are an increasing threat to our system, and we need to better predict, assess, and mitigate wildfire risk in all the North Carolina communities that we serve. Supporting customer growth and expanding capacity to serve a growing service area. North Carolina continues to be a state experiencing steady population growth with no signs of slowing down. Since the last North Carolina rate case, we have added more than 85,000 DEC customers and more than 70,000 DEP customers. Our system has seen new record peak loads in 2024, 2025, and 2026. The bottom line is that for non-historic temperatures, we are seeing historic peak loads across the Carolinas. We must be able to support rapid growth from increasing population, advanced manufacturing, and other new customer growth. Distributed resource integration. This is about personal consumer choices, driving the needs on the grid, and how do we prepare the distribution portion of the grid. Technological advancements in renewables and DERs are reality on our grid in North Carolina, driving the need to manage two-way power flow. DEC and DEP are making great strides on the grid improvements needed to address the external factors that are shaping the electric grid here in North Carolina, and the customers are seeing the benefits. But there are additional customers that we can deliver similar benefits to. The center of the slide provides some highlights of the progress being made so far. We have tripled the number of North Carolina customers served by the self-healing since 2022. More than 130,000 distribution poles have been replaced, and 15,000 transmission wood to steel pole conversions have been completed. More than 6,000 miles of distribution lines have been upgraded or replaced over the last 5 years. Approximately 340,000 hazard or danger trees were removed in 2025 alone. And 5 red zone projects or red zone improvement projects have been completed. So finally, the benefits to customers, automation and technology. In 2025 alone, self-healing avoided more than 1.2 million customer outages and saved 2.8 million hours of outage time for our customers here in North Carolina. Storm hardening and grid resilience. No upgraded transmission poles failed during Helene. To date in MRP1, we've completed 280 projects across 25% of the North Carolina substations. And supporting growth, serving 150,000 new customers in the last 2 years for the 2 utilities combined here in North Carolina. And most notably, all of these advancements I've just described have been made while safely operating the grid and keeping the lights on for our customers. I'll now shift into an overview of the distribution projects. I'll cover 7 areas: the benefits to customers, the grid capabilities, the overview of the work streams and programs and distribution projects, our planning approach to maximize customer benefits, an overview of specific DEC and DEP MYRP projects in our triad and coastal zones. I'll also talk about the methodology for our financial cost-benefit analyses. And lastly, I will highlight the programs that make up our MYRP projects. Before I shift into those 7 areas, I want to talk briefly about how we will be delivering the benefits to customers and establishing and/or strengthening the grid capabilities that are needed. I'll explain this more as we go along, but I want to introduce it here as we get started. Our projects are planned for a set of geographically clustered substations. Each substation, based on its specific circuit needs, will receive selected distribution programs. It is not one size fits all for each substation. Work is executed geographically to maximize resource efficiency, minimize disruption to customers, and deliver customer benefits across a broad customer footprint or area as we complete each project. The MYRP projects will result in tangible benefits to customers. First, reliability, fewer and shorter outages. Resiliency, protecting against physical and cyber attacks and severe weather impacts. Access to renewables and DERs. MYRP projects and the grid capabilities they bring are foundational and support future technologies. With enhanced automation and control and situational awareness, we will operate the grid more efficiently and support new customer programs and offerings, giving customers more control and affordability options. Our strategy will serve customers into the future. As I said above, these projects are foundational. Ongoing now in MYRP 1 and continuing to expand to even more customers across North Carolina in MYRP 2. The programs in our MYRP projects truly make the grid more flexible and adaptable. Self-optimizing grid creates new circuit connectivity and that enables two-way power flow. Automation and control technologies generate and capture huge amounts of data that we have not had previously. This is extremely helpful for our grid operators, but also for our planning engineers as they analyze and model our grid for future improvements and capabilities. Grid technologies will continue to advance and will be integrated into new solutions to address changing customer needs. There are 4 grid capabilities that deliver customer benefits. First being reliability. This has always been important, but even more so now and in the future with more people working remotely post-COVID, home-based businesses, and remote learning days for school children. Increased resiliency by strengthening the grid against infrequent but high-impact events as well. Capacity, increasing line and substation capacity to support load growth here in North Carolina. Automation and communication. This is about resiliency, and the poster child for this is self-optimizing grid. It detects faults, reroutes power, and minimizes that impact to customers. And lastly, voltage regulation, maintaining proper voltage with ever-increasing loads, and DERs and the associated intermittency requires more precise voltage control. I'll start with an analogy here about the 4 grid capabilities. If you think about the car that you may have learned to drive in or rode with your parents or grandparents as a young child versus what you drove to work today, or that may be sitting in your garage at home. For example, on newer cars, adaptive cruise control, radar and other sensors to maintain following distance. Now, some new vehicle features may feel like gimmicks. So while this is an analogy, the technologies that we are deploying deliver real benefits to customers as I described. There are 4, so we'll talk about DEC first and then DEP. For DEC, there are 4 categories of distribution grid improvements. You see these in the stacked bar graph on the far left. Those starting from the bottom are substation and line, retail and system capacity, hazard tree removal, and then integrated volt var control or IVVC. This totals approximately $1.6 billion for distribution across the MYRP period. The bar just to the right of that provides a further breakdown of the projects that are within the substation and line projects on the far left. These substation line projects are approximately $1.2 billion. There's a short description of the work embedded in those on the far right. We'll talk about that in more details on subsequent slides. But first, I want to explain why you see capacity as well as hazard tree removal as standalone work on the far left and also within substation and line projects there to the right. Capacity first off. This is a similar type of work in both cases to support traditional load growth and prevent thermal overloads. On the left, that work that's been identified as just not geographically located adjacent to or near a significant amount of other program work for consolidation into a substation and line project. However, within substation and line, that capacity work that's been identified is aligned and grouped, in other words, consolidated with a significant amount of other program work that is all executed together, again, for resource efficiency and maximizing benefits to customers across a broad geographic area. Hazard tree is very similar. The work is removing hazard trees is the work in both cases. On the far left, it's the traditional identification and execution of this work that is aligned with our normal maintenance trimming. So the work is done alongside the normal maintenance trimming. Within substation and line, the hazard tree is aligned and grouped again with the other distribution work to be executed in a more efficient manner as we do that work on an individual substation. A very similar view for DEP. Again, on the far right, substation and line, retail and system capacity, and hazard tree removal are the main categories. That totals for DEP to be $1.4 billion across the MYRP period. And the bar graph to the right is a further breakdown, just as we had in DEC with the substation line projects. That makes up the majority of the distribution projects at 1.1 billion. Again, short descriptions on the far right and very similar descriptions of the reason that capacity shows up in both standalone as well as in substation and line, as well as hazard tree in this case. So very similar to DEC. So I want to talk now about how we plan and then we sequence our substation and line MYRP projects. At the center of the circle, you see the two groups that are mainly involved in this, that is asset management for distribution, as well as our project development team. On the left side of this graphic is really the analysis at the circuit level. And the right side is an optimization of those plans at the system level. Starting in the lower left, we analyze each circuit. Those four critical grid capabilities that I spoke of earlier: reliability, capacity, automation and control, and voltage regulation and management are evaluated at the circuit level. That produces a gap analysis that we align proposed programs or combinations of programs to close those gaps at the circuit level. We then define that closure plan for that individual circuit. Then moving toward the right side, this is the optimization where we mold a comprehensive solution into an executable plan. We iterate against constraints such as labor, material, and budgets. We sequence individual substation projects within the operational zones at the area level. And I'll describe more about that in a moment. We also then aggregate the substations at that area level for our distribution MYRP projects. Let me describe the operational zones and areas that I just spoke of. Across the Carolinas for both utilities, there are 8 operational zones, 2 of those being exclusively in South Carolina, with the remaining 6 being here in North Carolina. And those zones from west to east, the Mountain Zone, then Central and the greater Charlotte area, the Triad Zone, Triangle North, Triangle South, and then finally Coastal, along with Wilmington. Each of those 6 zones that I just described is divided further into operational areas. There are typically 3 per zone, with the exception being the Central Zone and the greater Charlotte area has 4 from that perspective. So our substation and line projects are within those areas that are subsections of our zones. So what you see here on this slide is a DEC sample project. This is an actual project that was filed as part of our application. And I introduced our project-based approach earlier, but I want to reiterate it here. For distribution system, projects are planned to a set of individual circuits and their substations. We select the appropriate programs to close those gaps, and then we implement that and execute that at a set of geographically clustered substations. And again, that is for maximizing resource efficiency, minimizing the disruption to customers, and delivering benefits across a broad footprint. I'll start with another analogy and think about maybe a house remodel. There's 2 ways or 2 bookends of ways to do a house remodel. One might be what I'll call the do-it-yourself model. Lots of individual small projects. It likely takes a long time. The future projects that you do may cause some rework of previously completed work or former projects. It's less efficient. And the disruption and inconvenience seems to go on forever. And it's also harder to really extract and appreciate the benefits doing each individual upgrade over time. The converse of that is an aggregated overall project or a general contractor model. You identify all the things that need to be changed or upgraded. You hire a general contractor, maybe an architect or designer. You plan and schedule all the work as one large project that is properly sequenced. This helps to minimize any rework with sequenced trades and their tasks. It's still disruptive and inconvenient, but it has an end. There's a project schedule with a critical path. And once completed, all of the benefits are there to be enjoyed as you finish. Each remodel needs are different. That maybe it's energy efficiency or modern convenience or aging in place, just like each of the substations that we've analyzed, and we have projects built around those. So in the large graphic there in the table, this is actually one of our substation and line projects. The name of the project is in the upper right of that box. This is Triad Area 252. I described those areas a moment ago. Specifically, this is in the Greensboro and High Point area. You'll see down the left-hand side of the graphic, there are 8 substations listed with their names. And then the improvement programs are listed across the top for each of the columns. Let's specifically look at Holly Hill Retail. There are 7 different programs identified, again, based on that specific analysis that I described earlier for Holly Hill and its circuits. This is identifying the needs of this substation and its circuits for the next 3 to 5 years. This is a reasonable horizon to allow flexibility for future capabilities and needs while bringing benefits to customers in the near term. We'll now look at a similar project for DEP. Again, a substation and line project. The top of the project name is in the upper right of the box. This is in our coastal area 280. This is our Cape Fear, Clinton, Maxton, and Whiteville area. In this instance, there are 15 substations in that area where we have identified work to be done. Again, you see the names of the substations down the left-hand side and the improvement programs across the top. In this case, toward the bottom, we've highlighted the Vander 115. In this particular case, there are 8 different programs identified based on, again, the specific needs of the Vander 115 substation and its associated circuits. And again, this is work to be done over the next that'll provide benefits, or the needs that are identified are for the next 3 to 5 years. And this, again, a reasonable horizon to allow flexibility for future capabilities and needs. So our financial cost benefit analyses methodology. Overall, the benefits and cost benefit analyses used the same methodology we've used in previous filings, including our MRP1. This includes expected financial benefits, the vast majority of this being customer benefits of reliability, and this is the monetized value of not having an outage from the work performed. And these are also done at the program level. The data inputs, our planning inputs, we aggregate resource and input requirements, and these link back to the planning process that I described a couple of slides ago. We also look at substation and circuit characteristics. I mentioned the grid capabilities that are analyzed: reliability, capacity, automation and control, and voltage regulation. We look at historical recent project data, our labor and material costs, as well as labor hours and durations to perform this work, so we have the most accurate for schedules and cost. Our CBA inputs, these are the expected reliability improvements based on performing this work. This is based on the historical performance of the circuits themselves, as well as the historical improvements we've seen by doing this proposed work on those particular circuits. As we go through the future slides, you will see benefit cost ratio differences from DEC and DEP. The main driver for this is the historical SAIDI for each utility, and also at those individual circuits for each utility. And also the benefits, the percent reduction in SAIDI that will be achieved, or improvement that will be achieved by doing the work. So again, historical is a major factor, and the percent improvement based off that historical also. And lastly, a benefit cost ratio greater than 1 means the benefits are greater than the costs. For what I described around the historical SAIDI and the percent reduction or improvement, I want to share another analogy. If you think about maybe you're trying to increase the performance of an engine, and your choice of improvement is to add turbocharging to that engine, and the turbocharger you're going to use will add 50 horsepower. If you start with a 100 horsepower engine and place a 50 horsepower improving turbo on it, that's a 50% increase or improvement, very much like the SAIDI improvement that I talked about a moment ago. However, if you start with a 200 horsepower engine and that turbo addition again adds 50 horsepower, that's only a 25% reduction. It's still 50 horsepower, but again, the percent reduction or percent improvement is what we're speaking of. So that'll drive a lot of the benefit cost ratios, and I'll talk in more detail about some of those as we go through. Next, our methodology for the benefits and cost. We calculate the program costs from historical project data. I touched on that a moment ago. Historical, but recent material and labor costs. We calculate the benefits And again, specifically, the customer benefits are from the reliability using the interruption cost estimating tool as a data input. We also leverage the project schedules for the timing of the cost to be incurred, as well as when the benefits will begin to be realized. And lastly, the CBA itself, or cost benefit analysis itself. We tabulate the schedule of costs and benefits, the benefits again being outage avoidance, both sustained and momentary, as well as any operational savings from not having to restore an outage. Also the cost, the capital, including contingency, as well as implementation and ongoing O&M costs. The present value is calculated for both the cost and the benefits, and these are then netted against each other to determine the benefit cost ratio. We have also included a sensitivity tab or analysis tab where we range the cost higher and lower, as well as the benefits higher and lower to look at sensitivities of these analyses. So I'll now shift to the actual program overview slides. The format that you will see for my remaining slides will be very similar. There will typically be a first page where I'll describe the purpose and the description. There'll also be key details for this particular work on the right in a box, being the costs, both capital and O&M, project and service dates, as well as construction timelines. Generally, the second page will speak to the benefits to the customers for this work, MYRP1 highlights, as well as the grid capabilities that I touched on earlier, which of those are enabled, as well as House Bill 951 considerations. There are a couple of the programs that have additional slides for greater clarity and more detail. So we'll start with self-optimizing grid. This is a cornerstone program for distribution, and this program uniquely addresses multiple grid capabilities. And you may also have heard the term smart thinking grid. The analogy I'll use for this work is it's like a GPS for the distribution grid. Just like a GPS will identify traffic congestion and provide a suggested automated route for you to get around the problem, this work does the same thing for our distribution grid. When there's a problem on the grid from a fault, it will reroute power automatically around that problem. There are three major components to this work. The first being capacity. This is similar work to the capacity I'll discuss a little bit later. But in this case, the additional capacity is for self-optimizing grid to provide an automatic backup for an adjacent circuit, not just to serve native load and avoid a projected thermal overload. To do this, we also need connectivity or ties between individual circuits. Those need to be created if they don't exist or strengthened to support the load transfer. And lastly, automation. These are the intelligent switches in the field, as well as the control software in our control centers that convert the distribution grid into switchable segments that minimize the number of customers affected when there is a fault. So this slide is actually a close-up view of the graphic that was in the center of the previous slide. And this is a before and after schematics for a self-optimizing grid network. This is in our Greensboro area, just southeast of the Piedmont Triad Airport. In this particular case, if you look at the graphic on the left, on the far left, you see the two circuits involved are the Friendship 2405, as well as the Fairfax 2410. And those are represented by the brownish orange circuit toward the top and the blue circuit being the Fairfax 2410 starting at the bottom. The boxes that are along these circuits, both the red and the green, these represent the automated switches that are actually deployed out in the field. So this is the before picture on the left, and the average number of customers between those switches is 1,016. In the very center of the picture, you'll see a lightning bolt graphic with a cloud. This is to represent a fault on the circuit at that point. And with that fault in the location that's identified here, 1,525 customers will be out of power. So again, with the fault in that location prior to self-optimizing grid, 1,525 customers that are out. If you look at the graphic on the right, this is after we've deployed the segmentation for self-optimizing grid. These are the same two circuits, but you'll notice there are many more switches, and that is the SOG segmentation that's been deployed. Now, instead of 1,016 customers on average between those switches, there's 407 is the average on these two circuits. If we apply that same fault in the exact same location, in this case, only 433 customers would be out of power. That is 1,092 customers that did not have an outage after we deployed this system. This requires zero human intervention. The DCC operators will see this happening on their monitors, but again, the system switches around the fault automatically. It detects the fault location It sends switching commands to those devices and minimizes, as you see in the example, the exposure to the fewest number of people possible. And this happens typically in less than 60 seconds. So these two SOG circuits on the screen are actual SOG circuits. This isn't just a diagram. These exist in the field. There's about 6,500 customers on these two circuits. Since we first deployed self-healing technologies on these circuits through the end of 2024, this system has saved over 21,000 customer outages for these customers and avoided more than 6.5 million minutes of customer outage time. That's more than 108,000 hours of outages avoided just for these two circuits. I'll leave another analogy to describe self-optimizing grid. Think about a bicycle wheel. You've got the center hub of a bicycle wheel, the spokes going out to the rim. Now think about a spider web. Spider web also has a center. It has the radial parts of the web that go out to the door frame or wherever the spiders built the web. But then there are dozens, if not hundreds, of connections between those individual spokes. And think of those extra connections that I described in the analogy on that web as being more options to reroute power, as you see with a self-optimizing grid. So I've talked about the benefits on the previous slide with that real example, but in summary, it improves reliability and resiliency. It reduces the number of customers that are impacted when we have faults or outages. It also reduces the number of outages and decreases the duration of those outages. You see the benefit cost ratios there in the very center, the far right box there. And I described earlier where you'd see differences between the two different utilities. DEC being essentially a 4 benefit cost ratio of 4, where DEP being approximately 6.5. This goes back to what I talked about earlier, the historical SAIDI for each utility and its associated circuits, as well as the percent of improvement by deploying this capability for those. I mentioned earlier that SOG addresses multiple grid capabilities, and you see those listed on the far right in the upper box. So MYRP1 highlights in the lower part of the graph, and I'm going to start on the left, bottom left. First off, you see some acronyms, CI and CMI. CI represents customer interruptions, and one customer interruption is a single customer having one outage. And CMI is the customer minutes interrupted, where again, one CMI is a single customer out for 1 minute. The real takeaway here is at the very bottom there under that table. Inception to date for self-optimizing grid through the end of 2025, we have avoided over 775 million minutes of outage time for North Carolina customers. That's approximately 13 million hours. And we've also moved to have for DEC, 79% of the customers underneath this automation umbrella. And in DEP, we've advanced it to 69% as well. So now, voltage regulation and management. This is not new and continues to be required to support increasing loads, but the impact of DER necessitates increased functionalities and capabilities in this area. This program installs new voltage management equipment and upgrades controls on existing voltage management equipment. This supports load growth, as well as maintaining and improving power quality for customers. There are 3 types of assets deployed: voltage regulators and upgraded controls. Those maintain proper voltage levels and respond to fluctuations from normal load variations and DER intermittency. Capacitors to provide reactive power support, which complements the voltage support from the regulators. And lastly, power electronics for voltage and reactive power support in areas of particularly high DER penetration. Regulators and capacitors are not new, but upgraded controls for two-way power flow and new functionalities are. Power electronics, however, are newer and provide instantaneous voltage and reactive power support. Think of regulators and capacitors as coarse adjustments and power electronics as fine and instantaneous adjustments. So the benefits of voltage regulation and management are improved voltage experience, both maintaining proper voltage levels, as well as reducing and mitigating power quality issues. MYRP1 highlights at the bottom for DEC, the conservation voltage reduction mode. It will be fully operational at the end of 2027. And to date, the CVR megawatt hour savings for our DEC customers is 191,000 megawatt hours. For DEP, the conservation voltage reduction capability will be fully operational in 2028. And to date, there's been 38,000 megawatt hours saved for customers. Capacity. Capacity upgrades are needed to support growth from traditional loads as well as electric vehicles and integration of DERs. So there's broken into two different types of capacity on the slide, retail capacity and system capacity, and I'll describe the difference between the two. For retail capacity, this is upgrades to our retail or transmission to distribution substations. We use the word retail since these substations are the ones that serve distribution's retail customers as opposed to wholesale customers that are served by transmission. This work includes substation power transformers, upgrading those or adding new transformers, breaker additions for new circuits outside the station, and potentially new substations if the substations in that area are fully loaded. Think of this work for retail as being work done inside the substation fence. System capacity. This is upgrades to the actual distribution lines or circuits themselves, so between the substations and the customers that we serve. This includes upgraded wires or conductors, as well as equipment, as well as new circuit additions also. And think of this work as outside the substation fence on the distribution grid. Capacity benefits are improved reliability and resiliency. This reduces potential outages due to overloaded equipment or conductors, and it mitigates outage risk associated with high demand periods. Capacity improvements can also be leveraged by our self-healing technologies. It does expand solar or capacity enables two-way power flow, thus supporting additional renewables and beneficial electrification. MYRP 1 highlights you see at the bottom, capacity assets that were placed in service through year-end 2025 for both DEP and DEC. These are the inside the fence improvements of new substations, transformer bank additions and upgrades, as well as new circuits. And at the very bottom, the system work that's been done in MYRP 1 of circuit upgrades for conductors and equipment. Hardening and resiliency. This work is focused and can cover focused in 4 areas and can cover a broad range of improvements and upgrades. It is designed to make the grid more resistant to outages, and when they do occur, enable faster recovery and restoration. This work has 4 focused work streams. First off, strengthening laterals. These are the tap lines off of our main circuits. Strengthening parts of the distribution grid vulnerable to extreme weather impacts from storms. Also, design upgrades to assets that are prone to damage from vehicle accidents or public interference. And lastly, for long duration interruptions, relocating segments of overhead circuit backbone from hard to access areas to more truck accessible locations. So first off, before I talk about laterals, another analogy, think of, this is a roadway analogy. Think of the transmission system as the interstate highway system. When I talked about the backbone, that would be more for the self-optimizing grid. Think of that as the multi-lane suburban or urban highways or boulevards. And laterals, what I'm about to talk about here, will be those side streets off of the main boulevards or laterals that serve the neighborhoods. For laterals specifically, this is a data-driven approach looking at outage history on those laterals, looking at specific cause codes. The physical condition of the conductor is also evaluated for damage, multiple splices, fraying, or other physical conditions. And the most common is an older vintage steel core wire with a corrosion risk, and that's upgraded to an all aluminum alloy. For storm hardening, this is also data-driven, looking at outage history, but focused on very specific storm cause codes in the data. And then a geographic analysis that typically is looking at our coastal areas for tropical impacts and our mountain areas for winter impacts. This results typically in larger and stronger poles, shorter spans, and additional guy wires for high winds and heavier ice loading. Next is public interference or vehicle accidents. Whenever I come to Raleigh or in Charlotte, it's typically on the morning news. You see multiple times a week on the traffic report of a vehicle that struck a utility pole, and the outages that occur in that area, as well as the traffic disruptions that also occur. In this specific case, also data-driven, but looking at outage history again, but again, specific cause codes for public interference. This is focused on our 3-phase only sections of the circuit to provide the most benefit to customers, and is based on the frequency of those events that we've seen historically. In this case, the solutions may result in a design change, potentially relocating the facilities or potentially undergrounding those. And lastly, long duration interruption. As I stated earlier, this relocates segments of overhead circuit backbone from hard to access areas to more truck accessible locations. That reduces restoration outage time, as well as it's more easily maintained in the future to reduce outage risk. The attributes of these targets are typically radial distribution lines that serve large groups of customers or entire small communities. They're typically routed through inaccessible areas such as off-road, swamps, mountain gorges, or other extreme terrain. They have consistently higher than average outage durations compared to other parts of our system, and those terrain challenges that I described a moment ago are exacerbated in extreme weather conditions. The typical solution here is to relocate these facilities adjacent to a road right-of-way. So here I've got an example of a long duration interruption. This is in the Marshville area, southeast of Charlotte. The substation is in the lower left of the picture there. And the original circuit, 1201, coming from that station, is represented by the dashed red line that goes up at an angle through a heavily vegetated off-road route. The new solution was to locate that, co-locate that along with another circuit east along West Union Street, so toward the bottom of the graph from left to right, and then turning north along North Elm. Again, this relocated out of that heavily vegetated area for truck accessibility, as well as reducing the exposure to vegetation outages. For MYRP1, the highlights there in the lower right, we've completed H&R projects across all 6 of our North Carolina zones on 280 of our North Carolina substations. That's approximately 25% of our stations. And in DEC, that's been done on 280 circuits, and those circuits serve over 370,000 customers. In DEP, we've done this work on 205 circuits, serving approximately 350,000 customers. So the benefits for hardening and resiliency, overall for all 4 areas, this is about reliability and resiliency. It reduces the risk of outages due to conductor failures for laterals, severe weather for storms, vehicle accidents for the public interference, and long duration interruptions for those inaccessible areas. It increases grid strength, our modern conductor and design construction standards, more robust design and construction standards for storm, as well as relocating, undergrounding, and design changes for public interference. And lastly, relocating for better access and more robust design and construction in long duration interruption. Overall, for all 4 subprograms, upgrading historically outage prone assets lessens the quantity and duration of outages during extreme weather as well. This is a little bit of an eye chart, but this is the benefit cost ratios and their analyses for all 4 of these subprograms within H&R. This one, you'll also note some differences between these 2. Again, a couple of them are more pronounced than others. At the very top, the lateral hardening upper right, the DEC benefit cost ratio for lateral hardening 1.03 versus DEP for 5.33. This goes back to what I described earlier of the historical SAIDI for each of the utilities and their circuits, as well as the percent improvement expected by this specific work in those different utilities. And another one that you'll see a significant difference is public interference. In DEC, this has a benefit cost ratio of 4.18, and in DEP, it's actually less than 1 at 0.64. This still has that overall impact that I described earlier of the historical SAIDI, but there's also some specific things in the data that I'll share with you as well. In both cases, we identified about 50 devices with these outage histories from public accidents for both utilities. Where the differences start is in DEC. For those 50 devices, each device had of those 50 devices, there were about 20 outages per year from 2020 to 2024 versus 13 for DEP. So fewer outages in DEP as is the first factor. The bigger factor is the number of customers that were impacted by each outage. In DEC, that averaged 700 customers per outage, where DEP was approximately 200 outages or 200 customers per outage. So that's the main drivers for the differences on those. Hazard tree removal. This is a program that's within our overall integrated vegetation management program. It identifies and cuts down dead, structurally unsound, dying, diseased, leaning, or otherwise defective trees from outside of our maintained right-of-way. This maintains or improves reliabilities caused by trees falling from outside the right-of-way. Our right-of-way maintenance trimming program addresses vegetation inside the right-of-way. So why is this work important? Vegetation typically year over year is about 20 to 25% of all the outages our customers experience. And out of that 20 to 25%, approximately 50% year over year is from trees falling from outside the right-of-way. Again, these dead, diseased, dying trees that are outside of our maintained right-of-way. So the process for this work, the inspections are performed by a qualified Duke Energy representative using industry best management practices. Any trees that are identified that present an extreme risk to our infrastructure and the failure is imminent will be immediately mitigated. All the other hazard trees are assigned to one of our vegetation suppliers that do our maintenance trimming as well. They contact the property owner and customer, notify them of the work that we would like to do, and receive consent from those customers. Then the trees are cut down and that threat is removed. The benefits for for hazard tree reliability and resiliency. Again, this reduces the risk of outages, which is about 50% from outside the right-of-way for vegetation. It's a prudent utility practice. Our MYRP1 highlights there on the bottom of the graph toward the left, the miles that we've assessed for hazard trees in both DEC and DEP in 24 and 25, as well as the number of trees that were actually mitigated in each utility per year. Equipment retrofit. This targets equipment that's prone to outages caused by wildlife interference, lightning, and spacing or insulation issues. The types of equipment that we specifically target in this work are overhead transformers, which is what you see in the picture there in the center, as well as arrestor locations and riser poles, which is where our overhead conductors transition from overhead conductor to underground cable. The typical work activities are installing local fuses, which limit the outage impact to only the customers served by that particular asset. We install animal guards and covered lead wires to mitigate animal interference. And porcelain lightning arresters are replaced with modern polymer lightning arresters to increase insulation level. And lastly, replacing metal brackets in these installations with non-conductive brackets. The benefits of equipment retrofit: it reduces outages. It minimizes the number of customers that are impacted by a specific equipment outage, and modern construction specifications help to speed restoration when required. There is again the outage cost avoidance from fewer outages and the improved customer experience from better reliability. In this case, you also see differences at the very bottom there toward the right, the benefit cost ratios between DEC and DEP, 1.35 for DEC and 8.74 per DEP. There's a linkage between these two benefit cost ratios you see and the difference between those and the MYRP1 highlights that's just to the right of that. So let me explain. So if you look at the box of the MYRP1 highlights, you'll notice that in that one, transformers, which is the top line there, that's the highest volume and quantity asset for both DEC and DEP. Again, you see that with the number of 31,000 done for DEP. But looking at MYRP1 for DEC, this work was essentially already completed for transformers. That's why no work was identified in MYRP1, and you see the NA there. Specifically also for DEC, for riser poles and arresters, more analysis was needed. So this work was held in DEC for potential inclusion in MYRP2, which we have now done. So the reason for the benefit cost ratio being higher for DEP: one, DEP did not historically have these construction standards for these installations, transformers, riser poles, and arrestor stations. So the SAIDI improvement for DEC is much higher than historical for these particular installations. There is still transformer volume remaining for DEP. So the greater percent SAIDI improvement shows up in the benefits. If you look at the benefits for DEP, substantially more, I think it's $685 million compared to DEC. The DEC benefit cost ratio is still beneficial for customers, and the vast majority of this work in DEC is riser poles compared to transformers, which are complete. Infrastructure integrity. This is about proactive identification and mitigation of risk to the distribution grid. This includes end of service assets, and that is based on condition of those assets as well as end of life, technological obsolescence as well as upgrades, and removal or replacement of damaged in-service assets that are still in the field. This is about planned upgrades, improvements, and replacements to minimize customer impacts. And again, a potential unplanned outage avoided by doing a planned replacement is the benefit here. Examples specifically, inspection-based asset replacements, think of poles and oil field equipment, oil mitigation via solid dielectric recloser upgrades such as we deploy in self-optimizing grid, technological obsolescence, control panel replacements for devices to include cyber, functional gaps, as well as no support from vendors for older models. And lastly, communication and automation, where legacy devices are upgraded to SCADA-enabled devices such as we do in self-optimizing grid. Infrastructure integrity benefits. This reduces the risk of outages due to unplanned replacements or failures, and sustained infrastructure integrity enables more efficient restoration. I talked about a house remodel installation or analogy earlier, and you can liken this work to doing a renovation where you're renovating your living space, but there are foundational issues that need to be addressed, such as a settling, cracking foundation, or water seepage. This work needs to be done to support the other work that we're doing from assets that are showing degradation. MYRP 1 highlights there in the bottom, the miles of underground cable that have been replaced, as well as pole replacements based on inspection and circuit surveys. That concludes the distribution portion of the presentation. Happy to take any commissioner questions.
Thank you, sir. I do have a few questions here from commission staff that I'd like to present to you, and then we'll open up the floor for additional questions from commissioners.
Sir.
Mr. Guyton, this is more of a big picture question. Can you conceptualize Duke's proposed distribution spending in these transmission and distribution filings with their historical spending?
So I can only speak to distribution, but
Okay.
I don't have the numbers in front of me from historical. This type of work I can say though is work that we've done historically. We've been doing self-healing type activities as an example since the 2010s, as I described from that perspective.
All right. And one other big picture question, in terms of identification of transmission distribution projects, is the overall methodology still the same as the last multi-year rate plan, or were there any new innovative techniques used to identify these projects?
So I would say actually a little bit of both. So for MYRP 1, and we had some extensive discussions with public staff over this, we leverage what we call our grid plan, where we do an analysis of all the circuits across the Carolinas. Of course, for this particular proceeding, we're focused on the North Carolina circuits for both utilities. That grid plan was used again. However, it was refreshed with all new data for this particular filing. So same methodology, but updated data, including, I talked about this earlier, recent historical costs that we've seen for doing this type of work, as well as durations, to be more accurate with our cost estimates as well as project schedules, and updating benefits as well. I guess this is one I'll touch on also. We've also used the interruption cost estimating tool. We did that in MYRP 1 for our benefit cost ratios and analyses. We've done that again. However, we're using an updated version that's been released, ICE 2.0. And this actually has some specific Duke Energy customer survey data included in it. So an upgrade to our information that we use in that, but same methodology.
Okay, well, that actually is a nice lead into the next question, because I believe that was released in March of 2025. Is that right? The new ICE calculator?
That sounds right. Yes, sir.
And of course, I guess there were 26 utilities, as I recall, that kind of participated in that nationwide survey, and it included Duke territories.
Correct.
So what exactly information did Duke share that was a part of the analysis that went into coming up with the new ICE calculator for 2.0?
Did you ask what information did we share? Or?
Yes. And how was that done? How was that, if you could get into more detail?
So I can't share a whole lot more detail. There
Okay.
are some subject matter experts involved in our company that could provide a lot of detail on that, but I know that it did provide, one of the things that I can remember that it provided was, I think in ICE 1.0, there was a limitation to the duration of outages that you could model. I think it was limited to maybe 8 hours or maybe 16. There's now a 24-hour duration, so we can model much longer outages in that as well. And in fact, in our data that we've used for these CBAs, there's a section that has what I'll call typical reliability data, non-major event days, but there's also major event day data. So Helene and Debbie are actually included in the data that analysis we've used in this as well.
All right. And as I recall, it was like Lawrence Berkeley National Laboratory and Resource Innovations that was involved with this update. Did Duke play any meaningful role in meeting with them, or what was Duke's involvement?
So we were actually a participant. I think that's
Right.
the right term to use in that. And so I don't know what those meetings were like. I wasn't a participant specifically, but I don't know how many utilities actually participated with LBNL and the group doing the update, but Duke was one of those folks providing input and feedback.
Yeah, I think it was 24. I think I might have said 26 earlier, but
I think you're right.
okay. Now let me ask you this, and this is more detailed information, but on page 2 of DEC's exhibit TC5, it shows outages and port customer interruption savings of 10,696 in 2027. In 2028, it was 51,418. And in 2029, it was 66,013 and upward, with typical durations of 3.9 hours, 3.06 hours, and 3.09 hours respectively. How were the number and duration of outages estimated for these individual projects?
Can you tell me, I know you're on TC5. Can you tell me the page number again? I'm sorry.
Yeah, it was page 2
Page 2.
of TC5.
And you were looking at,
It's, yeah, of course, exhibit TC5.
correct. I'm on that page.
All right.
And you're looking at outage durations?
Yeah, well, exactly. And it gets into all the customers' interruption savings. It was 10,696 in 2027, 51,418 in 2028, 66,013 in 29. These. And of course, the durations are 3.19 hours, 3.06 hours, and 3.09 hours respectively. So the question was, how were the number and duration of outages estimated for individual projects?
So these are actually, our cost benefit analyses for distribution are at the program level.
Okay.
And not at the specific project level from that perspective. So there's a cost benefit analysis for self-optimizing grid, then hardening and resiliency, the laterals, not the specific part. So this is looking at, does this type of work provide value to customers is what we're looking at here. And then we do the analysis for individual substations and circuits to say, does this make sense to deploy that there?
Got it. So in this case, you're looking at the program versus the project level.
Yes, sir.
All right.
And that's true for all the CBAs.
Okay.
For
Now
distribution.
Now the ICE calculator shows a different value for customers who experienced an outage in the last year versus those that did not. For those with medical needs to electricity versus those without, in addition to other variables. What tailoring, if any, did Duke do to the calculation of residential and non-residential outage values?
I would have to take that back to our CBA and ICE calculator experts. I do not know the answer to that.
Okay. And I guess on page 2 of DEC exhibit TC5, under environmental benefits, it includes an increasing dollar value per ton for CO2. Why does Duke include a value for reduced CO2 emissions in its benefit calculations for this cost benefit analysis, but not for the CPIRP?
I can't speak to the CPIRP, but what I'm seeing, if I'm looking at the correct line here, it's around IVVC savings. And I'm looking for, well, it's just underneath the IVVC is where I see the environmental benefits. But I can't contrast that to the CPIRP.
Okay, that's fair enough. Now, on page 2 of DEC Exhibit TC5, reliability, it includes an increasing dollar outage figure for residential customers using a $15 outage for 2027. Can you explain the discrepancy between the residential outage value and Duke's rates? And you can get into this a little bit further because it was an interesting analysis that was done. Why would a residential customer be willing to pay $15 to avoid a 3-hour outage when they could be paying less than $1 for the actual service itself?
I don't know how the questions the survey questions were asked. And so I don't know the detail behind that, but it may have been, it seems like for business and or industrial customers or business customer, commercial industrial, they can calculate a loss of revenue, probably impacts their answer. For residential, I don't know if the questions to customers are more qualitative or quantitative, and the calculator interprets that something. I do not know the detail of that.
Okay. And the ICE survey asked the recipients if they would be willing to pay a particular one-time amount to avoid a single outage. Now, Duke's cost benefit analysis appears to include the same number and duration of outages each year. Please explain the discrepancy between the survey questions and how the survey was incorporated into the analysis, if you know.
I do not know, Commissioner. I'm sorry.
All right.
We would have to consult
And have to get into the person who actually was involved in those level of details and familiar with the
Yes, sir.
methodology, the survey, and what responses were elicited and how that was all put together.
Yeah.
Fair enough. And this kind of leads into some of the other issues as well. Duke's cost benefit analysis, such as that on page 2 of DEC Exhibit TC5, shows that commercial and industrial customers receive benefits from reliability improvements that are nearly 47 times greater than the benefits received by residential customers, despite commercial and industrial customers representing less than 14% of the customer base. How has Duke considered reflecting this discrepancy as it relates to cost allocation of these projects?
I'm not a witness for cost allocation.
You're unable to answer that.
I am not able to answer that.
Fair enough. And let me ask you this. How widely is the ICE calculator used to calculate the benefits of distribution investments in other jurisdictions? And that you should be able to answer.
And you're speaking of other Duke Energy districts.
Or other jurisdictions where generally.
Other utilities.
Yes, other utilities, yeah.
So I can speak specifically for these two utilities in South Carolina, because I've also been the witness in South Carolina. We leverage it there. To my knowledge, it's the only broadly available type of ICE calculator, interruption cost calculator, that I'm aware of. There may be some others that are out there, but I think this is the most widely used by utilities. I do not know how many use that, but you mentioned there were 24, I think, participants in that. So they would certainly be users, and I would think it'd be broader than that as well.
All right. Now, I had a few questions here regarding completion of distribution projects. What is the percentage of distribution projects from the initial multi-year rate plan that have been completed on time and on budget, if you know?
So there should be in what I'm referencing is an exhibit from my direct testimony where we talk about, look at my, give me just a moment, see if I can find
Sure,
it.
take your time, sir.
So for DEP, my exhibit 1A in my direct testimony is the multi-year rate plan 1 placed in service. Let me
And does that exhibit identify those that were not only placed in service, but also within budget?
Let me
Or
look and
does
see
it-
how the
Yes,
exhibit
see how
is.
that data, and
is
what was
set
that
up.
exhibit number again, if you could reference that?
It's exhibit for DEP, it's exhibit 1A.
1A, okay.
And give me just a moment. I'll look and see how it's laid out. See if it can answer that question directly. So you said on time and on budget?
Yes, that's the first component of the question.
So I see an actual in-service date. I'm looking to see if it has the proposed in-service date. In this particular exhibit, I am not seeing, no, there is, I'm sorry. There's an approved MRP in-service date, and then there's the actual in-service date. What I don't have is totals to your question, but the data is there.
Okay, so it has the proposed service date and the actual service date.
Yes,
Is
sir.
that correct?
And then cost, I'm looking to see if there's an approved cost. There should be. Let me make sure I can find it. And then the actual in-service amount. So I do see a settled estimate. And then there's an actual in-service amount as well. And I'm looking at let's see, I'm looking at I'm on page 2 of that exhibit for DEP.
Okay,
Line 25, and that one in particular actually went in under cost and actually on time, April 2024. And that's one line item out of that exhibit. Let me get you that same information for DEC, because that would be a
Okay.
separate exhibit.
that would be helpful. So it identifies whether they were completed on time or not, and there is data on that exhibit dealing with the budget as
Yeah.
well.
Approved costs from the commission order, as well as what it was actually placed in service at that project level.
All
And
right,
it's the same exhibit number for DEC for me.
so that would be exhibit 1A.
Exhibit 1A, yes, sir. And I'll make sure it has the same layout, but it should.
See if it has the same content, if you would, because I do not have your direct testimony before me at this time.
Yes, I see the approved dollars at the project level, and I see actual in-service dollars as well. And then, yes, there's an approved in-service date and the actual in-service dates. So that data does exist in 1A, my direct 1A
Right.
for distribution projects that I represented.
Okay, so for both DEP as well as Duke Energy Carolina.
Same exhibit. number, yes, sir.
Excellent. Does that same exhibit identify which projects are incomplete at this time?
This would only be ones that were actually placed in service
Okay,
by the information I'm seeing. So it would only be ones that are placed in service.
okay. So the ones that, since it only has the ones in service, the ones that are incomplete would by default not be listed on the exhibit.
And this is rate year 1. These 2 exhibits are for rate year 1 only.
Okay,
So we would have to supplement or something with a rate year 2
Got it.
information. So this is the very first rate year only.
yeah, so it would have to be supplemented to provide rate year 2.
Right. Let me
Okay.
look at my supplemental and see if we've
See if it's added there,
updated
perhaps.
that as well.
That'd have been a logical thing to supplement it, perhaps.
We did. Let me look at the date, maybe see the layout, but it's supplemental exhibit 2
Exhibit 2, supplemental exhibit.
in DEP. I think it'd be the same, but let me look at the layout real quick.
Would also be supplemental exhibit 2 for Duke Energy Carolina.
I will verify that. Give me just a moment. So for DEP, yes, there is a rate year 2 report. It appears to have the same layout, but let me look real quick. Yes, I've got settled costs. I see approved and current in-service dates. I'll need to verify. I'm seeing, there's a dollar column, but I'm seeing what appears to be some missing information here. But it should be exhibit 2 supplemental.
Okay.
We may have to correct it if there's some missing data. Let me look at DEC real quick.
So I assume you can supplement the record to provide.
If it is missing, we would supplement that. Yes, sir.
Okay.
By the time supplemental was filed for DEC, I don't believe we had compiled the rate year 2 information at that time when supplemental was filed. So that'd be in a future update.
Very good. If you could perhaps supplement the record with that information, that would be insightful.
And Commissioner McKissick,
Yes.
I'll add, these are also filed, the quarterly reports in the prior docket as well. But we'll
Okay.
supplement in this docket as well.
Thank you. All right, and I'll move on to one or two other areas. Of course, the idea of using customer average interruption duration index, or CAIDI, the momentary average interruption frequency, MAFI, there are additional reliability metrics that a few states require their utilities to add on to reports, in addition to what you all provide in terms of information. Is there some reason why you do not rely upon kind of the CAIDI index and the MAFI indexes?
So for Katie specifically, we file whatever is required by the commission, and if the commission, asks for that information to be filed, we would certainly file that information. What I would say at system averages, the SAIDI SAFI, and I'm talking about Katie specifically here, frequency gives you what impact are we having from the work we're doing, and then the CAIDI is really already embedded in the SAIDI. So you've already got a duration metrics there from that perspective, and so. I personally am not sure what the CAIDI value is. Operational groups may look at that, our operations teams, because that's more about crew response for specific events. But at a system level, I'm not sure what CAIDI would share that you don't already see in SAFI or maybe. And MAFI is really more of a momentary type activity from that perspective compared to a sustained outage.
Okay. So I guess what I'm surmising is that you believe the indexes that you use are better, accurate, more reflective indicators than those other indexes.
Certainly for CAIDI. I mean, MAFI's a different indicator. I won't say completely, but it's certainly different being a momentary as opposed to sustained outages. So SAIDI, SAFI, as well as CAIDI deal with sustained outages.
Okay.
MAFI's really in a different category.
Now, can you provide some explanation as to whether SAFI metrics have continued to fluctuate since 2019? Do you have any context for why that has occurred?
So did you say fluctuations?
Yes.
So, I mean, with all reliability indices, at least in my experience, there's a year over year annual volatility that occurs naturally. Typically, it's driven by weather. Is the most common factor in that, but there's an annual variability that's to be expected. The trends are what I would, focus on more. And in fact, kind of back to my direct testimonies for both DEC and DEP, there are 5-year charts for SAIDI and SAFI, not only with the annual values on a graph, but also the trend lines as well. And I believe I'll find the page number for you. In DEP, those two graphs of SAFI and SAIDI, and this data is 2020 through 2024, so a 5-year view for those. And there certainly is an annual variability, but the trend line for SAFI is downward in a positive way. SAIDI for DEP, the trend is slightly up, but if we brought in the 2025 data, it would probably flatten or be declining as well from that. And then, so that's page 12 in my DEP direct testimony. And there are similar charts for DEC in my direct.
Now, as I recall, there's a catastrophic event exception that's built into those. Is that right?
These are simply without MEDs. The catastrophic is not included.
Not
in
included.
in my testimony. No, sir.
Exactly.
There's a footnote, a pretty lengthy footnote talking about catastrophic, which
That's what I'm thinking about.
yeah, it's quite a paragraph on those pages. Yes, sir. And for DEC, those two graphs are on page 12 and 13, and you will see that footnote as well for those. But that was only in 2020, or thankfully so far we've only seen that 2024 due to Helene. Hopefully don't see that again, but that catastrophic exclusion is not included. This is using the traditional 2.5 beta IEEE method that we've historically used.
Got it. Okay, that's good to know. Thank you. Now, Duke's quarterly multi-year rate plan construction status report note that some multi-year rate plan 1 projects have been placed into service. What has been the reliability impact experienced by nearby customers as a result of placing these projects into service?
I couldn't speak to that at the, how do I say, at the project level or nearby customers. To try and do that analysis, we would have to look at, well, go back to the SOG circuits I described earlier. If we were looking at individual SOG circuits where we've deployed SOG, we'd have to pull that historical data for those specific circuits. But I think your question was worded about nearby customers.
Yes, that's correct.
So I'm not sure I follow the question. If we've done work on self-optimizing grid and it's those two circuits I represented, customers on a circuit next to those that aren't physically connected or aren't part of that SOG network, they wouldn't have benefit from those two. But they may have their own SOG circuit that they would be receiving benefit from that perspective. And one of the things I alluded to it, but specifically around MYRP2, the benefits I described for those two circuits there southeast of the Triad Airport, Piedmont Triad, the projects we're bringing in MYRP2 are extending SOG capabilities to a new set of customers that don't have that now. So this is another list of stations. If you compared MYRP1 stations with MYRP2, again, we're simply bringing these benefits to more customers across North Carolina.
Thank you. Now, Duke states that its capacity and customer planning project summaries that the upgrades will enable interconnection of future resources like distributed energy resources. Are these for customer sited behind the meter DERs, utility scale DERs, or both?
So for distribution, the work that we would do, unless it's gone through the interconnection process, would be behind the meter.
Okay.
So more individual customer choice items.
And for end of life access, does it mean the end of the actual life of that asset, or does it mean the end of its depreciable life? So, I mean, or does it mean it's just obsolete? I mean, can you provide some context for how that's done?
Absolutely. So in the operations space, depreciation is important, but that's not something operational folks take into account. There's not we're looking at the actual condition of the asset. So if it's a wood pole that we've inspected, it's actually failed a strength test. And based on the strength that exists, it might be tagged for immediate replacement, or it might be one that there's a longer time frame that we would build into one of these projects where we know it needs to be replaced, but it's not it hasn't lost enough strength where it needs to be replaced immediately. So the depreciable life in our operational projects does not enter into it. That's something more in accounting space.
It does not enter into the equation. You're looking at the asset itself.
The physical condition of the asset. And the other thing I would say is, another term that maybe I didn't hear it in your question, but a manufacturer suggested useful life. We think that's interesting information. We may take that into our calculus for how often we do inspections. But if the asset's performing or we can maintain it and extend the life, whether that be in transmission, I think you'd hear the same from transmission. We do that. It's not once it's depreciated, we replace it. If that asset's functional and we can keep it running for customers, we absolutely do.
Thank you. Now, Duke states that the projects in the infrastructure integrity category contain asset replacements based upon condition of end of life and technological obsolescence. And I think what you've done just now is provided more examples related to that. So I think you've kind of addressed that issue.
I'll offer a little more from a technology standpoint, because what I described, or the example I gave of a deteriorated wood pole, is a physical condition as opposed to something else. So I referenced this in my comments earlier. So the intelligent devices that we have out in the field, the reclosers for SOG, capacitors or regulators, they have controls at the bottom of the pole in a cabinet, a lock cabinet at the bottom of the pole. Typically, those are SCADA enabled, so our control room operators can communicate with those devices. They can pull reports, fault data, other information back from them. The controls themselves are microprocessor based, as you would expect. There's potential that older controls, I talked about two-way power flow on regulators. The newer controls actually can change or determine source and load side and have that alternate depending on power flow from that perspective. There's also potential cyber obsolescence where there may be a vulnerability for the control itself inside the cabinet, or the vendor no longer supports it. They're not issuing any more software or firmware upgrades. And so we've got a risk that if it fails, we've lost control of it for those. The functional obsolescence, unless we really need the functionality, we would tend to leave in place and just identify a maintenance replacement that if it did fail, we do it. But if it actually causes operational issues and for the control room or others, we would upgrade that more proactively.
And how do you prioritize which projects that you move forward with first?
In a global sense, or specifically around the controls that I was just speaking to?
Well, in a more global sense, but if you want to relate it specifically controls, that would be helpful for that as by way of an example.
I won't use the controls as an example. I'll use the reliability for customers because that's the most tangible benefit that we provide with our projects. So there was a slide I went through, had a circular diagram, talked about the analysis we do at the circuit level, and then optimize that to the system level. I also mentioned, I think it may be an earlier question, where we've leveraged our grid plan files that we've shared with public staff in the past in MRP1. We've had at least 2 calls that I can remember with public staff in this proceeding, talking through the grid plan and the updates that we've made to that. That very specifically looks at the reliability at the circuit level and what's that historical reliability been? What type of events have caused, reliability challenges on those circuits? And then we're looking for what of those 10 programs can provide mitigate that in the future. It might be self-optimizing grid. We may have seen substantial lateral outages or storm outages or public interference outages that may point us to specific solutions there. So overall, the prioritization is looking at the reliability of the circuit, individual circuits, and those roll up to an individual substations. Those would be the stations that we would look at first for solutions to deploy as part of this proceeding and futures.
Very good. And I guess the last question I have at this point in time, we'll open it up to other commissioner questions. And that's this, in terms of the class of estimates that you're using, I know there was some discussion about class 4 versus class 5 estimates. Which ones are you relying upon primarily moving forward with what you have presented today? And I know that from the first technical conference, and one of the reasons you have that supplemental filing 5 days before is because you guess the cost estimates. But which classification of cost estimates have you primarily relied upon and why?
So our whole project development process is to identify projects early and then continue to elaborate and refine schedules, costs, things of that nature, and benefits as well. For the distribution projects, there may be some exceptions, but I think for the most part, when we filed direct, they were at class 4 estimates, which is further in the development, more refined than we had in MRP1 when we filed. And certainly we had some updates and supplemental in MRP1. I'd have to check the actual class of estimate, but projects were more refined that we filed for distribution.
Okay. I know we're scheduled to take a lunch break at 12:30. Let me see if there are other commissioner questions at this time. Commissioner Brawley, Chair Brawley.
I wanted to get you to expand on some of the earlier slides, on page 7. There was a phrase, under, customer benefits, effective projects, expand access to renewable and distributed energy resources. You expand on that? You say DER, what do you mean?
That would be a customer choice, their own individual rooftop solar or something of that nature. The fact that as we build out SOG networks that I described earlier, that capacity for two-way power flow is to provide an automatic backup if we have a fault on the circuit. But the fact that that capacity is there, it's available or could be used for, when it's not being used for fault conditions, it would be available that if there were substantial penetrations of rooftop solar, the power backflow would not cause us a problem because we've got additional capacity. But that's not why we put that capacity there. It's a tangential or tertiary benefit because of other work that we've done.
But you're also talking about this might be batteries?
It could be, but it'd be behind the meter for the work that I described in that comment that I was making there about the benefits there.
Okay. So those are all behind the meter. So is that also what you mean on page 8 with the, on the capacity, increase renewable facilitation by enabling two-way power flow in more circuits?
So yes, the fact that we have additional capacity for automation, and the example I used a moment ago, it's there to transfer. So each circuit has its native load. It's how we have the circuits normally configured. It's the customers that are on there. In our capacity program that I described, which was probably the third or fourth one when I went through the detailed slides, that's looking at thermal overloads. That's really looking at native load. So is there additional load coming that would cause a problem on a conductor or a piece of equipment? With self-optimizing grid, we're essentially saying, okay, we need to do analysis that if this circuit went out, could we transfer all that load to this circuit here? Or maybe it's to multiple circuits. By doing that analysis, there's I'll say additional capacity for non-native load that if there were DERs when things were normal, that capacity would exist and not cause us operational problems from overloading a circuit from somebody's rooftop solar or combination of rooftop solar or something of that nature. That's what I'm speaking to. It's a tangential benefit. It's not why we do capacity work.
Okay, so when you're talking about rooftop solar, this is like a community solar where people are putting up and then you're taking power from them?
If they don't consume it behind the meter, that would flow back to us.
Okay, then under the voltage regulation, there was a lot of discussion there, disruptive supply pipe spikes and sags, optimizing voltage levels. That sounded to me like dealing with a lot of inverter-based resources. Is that the aim of that voltage regulation?
It's not the only aim. We have to do voltage regulation for even before inverter-based resources existed.
Mm-hmm.
As load increases or changes during the day, voltage regulation is an important part of that. And so that's the core of what we're doing there. What we're also recognizing really with the power electronics, but those are on a very limited basis where we see a high penetration on a particular circuit or station of inverter-based resources that are behind the meter would be that case. So those are rare.
Okay. Thank you, Mr. Thank you.
Commissioner Vanderhart.
So I'm struck that what we seem to be doing here is throwing a lot of good money after bad. I mean, I'm reminded by an analogy that a former Duke executive gave one time about, I've got 2 cars in my garage, one that works all the time. It might be paid for, and I might have to put more oil and do a little more maintenance, but it runs every time I want it to run. And I got another car that only runs sometimes. And instead of saving my money to buy a third car that runs 99% capacity factor and it's clean, we got tons of fuel for it. Instead, what it sounds like you're doing is buying 7 cars of this intermediate one so that hopefully one of them will go when you can. You'll distribute them around the state. Maybe there won't be some clouds someday. You'll go over there and you'll be able to drive it. And at night, you develop a hill system where you run it uphill at night so that it'll run back downhill in the middle of the night. Might use that to charge one of the other 7 cars. And your driveway now, instead of going one way, you got a 2-way driveway, and your lanes and your roads are now 7 lanes to accommodate surges. I mean, a lot of this is purely due to the addition of solar. You would agree with me?
No, I don't.
Do you have those costs disintegrated?
The projects that I'm.
In other words, if you didn't add any solar going forward, do you have the cost of how much of these projects you'd have to do? I mean, you say yourself in this presentation, it's due to intermittent power supplies, the voltage regulators. I mean, I'm sure you need some of it. Don't get me wrong. But I'm just trying to make sure that which is due purely to solar is then attributed to those solar resources instead of socializing them across the system. That's my main concern. But it does seem like we're going to amazing extent to try to accommodate an inferior technology at great cost. And I might add too, that if I kept driving the car that's old, but I have to put more fuel in it, more oil in it, you're not going to make any ROE on it. But if I buy 7 cars, you're going to make ROE on all those cars. And of all the hills that you're building and the 4-way, 5-way, 6-way. So I'm just concerned that we're not getting a sort of a fair shake from a ratepayer standpoint.
So Commissioner, what I would say is the one area that I talked about potential intermittency from solar was voltage regulation and management. That's the only
The
place.
SOG is not going to be required in your capacity changes to accommodate for capacity when you need it.
The SOG program is specifically for thermal overloads from traditional loads.
And from traditional loads, not from the I forgot to add the car that when it does drive, the solar car, it drives too fast. So I mean, you're telling me that the majority of those costs that you're talking about, and I'll ask you that later, is what you'd spend that in any event. That's what I'm hearing.
Yes, sir. And I'll give you an example. So
And you'll be able to give us those costs broken out in that way? When we get you under oath, I mean?
I'd have to talk to our experts to see if we can pull
That'd
that
be
apart.
good.
But I would say this, so if you look at, for DEP, exhibit TC4 as part of our technical conference, page 1, actually at the top of that page breaks down the different programs and the dollars that we spend there. So voltage management, while the vast majority of that work is for traditional voltage and capacitive support, it's less than $18 million out of a.
Yeah. But your SOG program, you say is not due to intermittent. Then you develop a new cost savings, this BRC cost savings that are savings that you wouldn't have to incur if you drove that first car. I mean, that's another, but you're sort of getting money for buying the 7 cars, and then you're getting money for all the fixes. And then you're telling us that some of those fixes are going to avoid some of the mishaps that you got when you got those 7 cars, and you ought to be happy because those are savings to the customer.
So the benefit cost ratio, the vast majority of those benefits is the customer benefit of not having an outage. That's
Yeah. But what I'm saying is would those customers have those outages if you hadn't added so much solar intermittent power on the system?
Yeah, the outages, if I'd looked at the outages or outage cause codes for the programs, it's not due to solar. It would be vegetation, it would be wildlife, it would be other factors, not from a solar perspective.
And it's not due to, for example, all the additional transmission and distribution lines you have to build to accommodate those distributed sources. And it's not due to the increased thermal cycling of your resources that are backing up your solar?
Not on the distribution system. We're looking at.
True. I'm sorry. I get ahead of myself. I'll let you go and we'll work down the line later. But I am concerned that a lot of this is just being added because of a problem that maybe we ought to just cut loose and go forward with dispatchable power until we get nuclear online.
So what in summary, I'll say for distribution, the benefit cost ratios that we've got, those are around that provide reliability benefits.
Yeah,
It's not around
yeah, but why do you have reliability problems? At least some of that is due to the intermittent sources that you got on your system.
But
You know, oh, are
I
you
don't see
going to
that
tell
on the,
me?
I don't see that on the distribution system.
Okay, all right. Thank you.
All right, and I would simply say to all commissioners, let's try to provide the witness, the person providing us information, an opportunity to answer the questions, as opposed to trying to answer them for them. And on that note, since it's 12:34, we're going to go ahead and take a break for lunch. We will be back here at approximately 1:35. Commissioner Gaida is next in the queue for questions. Okay, thank you.
Thank you.
Ida. Commissioner Guida, you are recognized.
Thank you, Commissioner. Just a couple of questions. So, Mr. Guyton, related to the SOG program, or for that matter, SOG along with any other programs designed to improve reliability, does the company have, assuming that you're looking at, there's different ways to measure reliability, you've talked about SAIDI and SAFE, does the company have ultimate goals for SAIDI and SAFE that kind of look at the diminishing returns associated with, say, making a certain expenditure to get one more SAIDI minute of benefit and that sort of thing? Could you say just a little bit about how you just kind of attack the reliability improvement investment?
Yeah, sure. So there is an absolute recognition that there's diminishing returns as you move further down in SAIDI, for example. So that isn't aware. I'm not aware of a North Carolina, DEC or DEP ultimate goal to drive to from that perspective. I think part of that's informed from customer feedback, from surveys and other information. There may be some benchmarking that our governance team does as well that informs some of that. I would say specifically, maybe more in this particular setting in North Carolina, I know that for MRP1, there is a SAIDI PIM. That's a downside only PIM that's there. I would expect that during MRP2, potentially there's, another round or set for SAIDI PIM in that perspective. So certainly that would be top of mind wherever that gets set. But other than that, I don't know of a hard number specifically in a SAIDI, for example.
Okay. All right. Is there a way for, I guess, this commissioner ratepayers to understand how how you view the investment, reliability investments in such a way that, you wake up one day and decide, it's actually really good and we don't need to spend money on making it better. Is there a, is that somewhere kind of in your goalpost or vision?
Well, I'll put it this way. I don't know of a number that fits that, but certainly as you drive, let's talk about SAIDI lower, it is going to flatten out. And I'll say, in the distribution system, we'll need to continue to make investments because the system naturally degrades over time, whether that be infrastructure integrity, conductor, everything we have is exposed to the elements, even the underground facilities that we have, and will need to be upgraded or replaced or maintained over time. And if we don't do that, then reliability would start to go in the wrong direction. So at a minimum, maintaining that. I do think that, self-optimizing grid is a significant positive impact on the distribution system. There will reach a point, at least, I'll say temporarily, and I'll say what I mean by that, where if you think about self-optimizing grid, not only do you have the intelligent switches, the control system, but you got to have the connectivity between adjacent circuits to be able to transfer load back and forth. There are parts of our system, especially near the edges of our boundaries, and I'm not talking about the DEC, DEP boundary, I mean to other utilities, munis, et cetera, where there's really not a viable alternate feed from a traditional poles and wires perspective. And at that point, self-optimizing grid, the way we envision it today, would not really be a good solution, or viable solution for that particular circuit or a circuit like that. Something like the microgrid that Mr. Thompson is going to talk about may be the ultimate solution there to provide a source as opposed to a poles and wire source. That really doesn't make sense in that perspective. So, that is out there somewhere where that exists. But also the system, when I said temporarily a moment ago, the system is constantly expanding. And so even at the edges of our system, if that starts to build up and become more populated, we'll naturally have more infrastructure in that area to serve the customers that are coming there. That may create some opportunities for SOG teams that don't exist today, but 5 years from now, 10 years from now, there may be additional infrastructure that it makes sense to do that.
Okay, thank you. You're under the different categories, the buckets. So one called infrastructure integrity, you've spoken to. So that's not an insignificant amount of overall investment. There's a few examples in there, but can you talk to which parts of that category are the classic types of asset management that you've done for many decades, and which parts of it are relatively new? Can you characterize that a little?
Certainly. I would say the vast majority of it is historical types of activities that we've done, replacing end-of-life cable, underground cable, certainly pole replacements after inspection from a strength standpoint. That's historical as well. I'd say the only thing that's relatively new, and I'd say it's not brand new, is controls. As we move more to microprocessor-based controls, those will have a life that's different than a poles and wires type asset historically. Whether that be, again, vendor support stops, or there's a cyber vulnerability or a functional vulnerability or gap that we have in that space. That's probably the newer portion, but of course, controls have been around for decades as well on the poles.
Okay, thank you. All right, I think I just have one more. So when you add equipment to the distribution system, kind of like some of the stuff you're talking about there, is there a, when you add equipment, it's a capital investment. And I guess I'll ask you, is there an associated O&M cost, future annual O&M cost that goes along with those investments potentially?
So the short answer is yes. There may be some exceptions. There's probably variations between different assets depending on what that may be. But yes, and that I'd have to go back and find it, but that is included in our information that we filed, is not only the installation O&M, but also ongoing O&M, I believe, is identified as well.
Okay.
As part of that. And an easy example of that would be with self-optimizing grid. Each one of those recloser controls at the bottom of the pole, currently our way of communicating those is via modem, cellular. And so there's a telecom cost to have that as an active source that we can talk to from one of our vendors.
Yep. Okay. And so you're saying that is included in your project evaluation when you look at the sum total of installing those investments?
That's correct.
Okay. That was going to be my question. Okay. Those are my questions. Commissioner?
Are there any other questions from commissioners? Commissioner Tucker.
Thank you, Commissioner McKissick. I don't know if my questions will roll over into Mr. Fogg's area, whichever the three of you can answer what I'm going to ask. And certainly if it's not involved in distribution and transmission, you can tell me it's another area. I'll be fine with that. I guess the upfront question I'd ask, and I guess this, Mr. Guyton, is yours because you mentioned it. You talked about, if I recall correctly, Moore County. Did you mention that?
I did mention that in my global comments.
Right.
Yes, sir, I did.
Yeah. How have you hardened those assets? And we've had, I don't recall another situation there, but how do you protect substations from a 30-06 or a gun or a rifle or whatever? Do you put steel covers in front of the coils or heat exchangers or whatever's in the substation? How do you do that? And what's happened there and what was the cost?
So I did mention that in my open comments, but that was a reference to a transmission thing. So I'll let Mr. Fogg
Right,
answer that.
yeah, I knew it'd probably go his way. He needed to answer something. He didn't say a word the first. Yes, sir, go ahead.
Right. So in terms of addressing some of the security issues that we saw as a result of Moore County, we took a tiered approach to substations, and a lot of that was installing devices like cameras and devices like radar detection to help more deter having events there. So there's not really a way you can stop a bullet, right?
Yeah.
So, but we're more looking at ways to deter that from happening again.
Okay, that's fair enough. I got notes written all over your pages. The money we're spending on transmission and distribution, is that because we didn't have but 1 or 2% growth rate in the 1980s and 90s, and we just did not upgrade the transmission line more than necessary? I guess that's open-ended. Is that correct? We're spending tons of money. I think what you got about, if I saw correctly, what, $2 billion, $1.9 billion?
So depending on whether we're looking at the tech conference projects or my overall testimony from that perspective, but I would say this, we certainly saw small load growth, in previous years. That certainly has changed. Even prior to the data centers entering the conversation, we were seeing growth in that perspective. If you look at my direct testimony, I've got a breakdown of for DEC and DEP, and I can give you a page number. There's a pie chart that shows all the capital that we've invested in distribution since the last case, the last time I was sitting here. And capacity and new customer work outside of MRP is a significant portion of that. I believe that in that overall capital for distribution, about 40% is in MRP. The other 60% is outside of MRP in our base case from that perspective. So, but yes, we are seeing growth. I quoted numbers of, I think between the two utilities in North Carolina, we've added 150,000 customers in 2 years from that perspective. So certainly not only growth, but load as well from that perspective.
I think North Carolina's probably rolling along at about 11 million folks now, or close to it.
I don't know what the number is, but it is significant.
Somebody told me we passed Georgia and Ohio. I don't know if that's a true statement or not. I'm going to ask something that kind of is distribution and kind of transmission. Did we have to utilize on peak load coal assets during Winter Storm Fern?
I don't know the answer to that.
Mr. Guy? Okay.
Likewise, I'm not sure what our generation mix was during Winter Storm Fern.
Mr. Holman, you can jump in here, sir.
Yes, sir. I can answer that question. We used all available generation assets during Fern and the subsequent storm the next week that were available to us that weren't out of service for either planned or scheduled outages. There were very few. There were none scheduled outages. We used everything we had.
Okay. And this is a lead-in question about transmission and distribution. On those fixed assets in the coal plants that we have to have or had to have to meet the Fern requirements for generation and transmission, are we spending any money at those coal plants to try to upgrade the transmission to make sure that that availability for peak load is available? Is there any requirement to do that? Or are we still just on the same old lines we've had for some of those 60, 70 years? Where are we on that, sir?
Yes, sir. I am not a subject matter expert in generation, but I know that our generation teams are looking at opportunities to cost effectively create margin within the assets that you're talking about.
Okay, so you're saying that's over in generation, not distribution or transmission. So you don't know whether we've upgraded transmission lines from the coal plants in any recent memory?
From a transmission perspective, where we see a need to upgrade, we'll perform those upgrades to be able
Okay,
to get
so
that
we,
generation.
okay, so we can keep them online. Let me think here.
And
Yes, sir, go ahead.
We're obligated when generation changes that even at one of our own generation sites, they have to enter the queue. And we have to study that incremental increase in generation to make sure that that's not creating issues for the grid in North Carolina or the broader grid. That's our obligation under the FERC Open Access Transmission Tariff. OAT is the
Okay.
acronym.
That's fair.
And then I've heard our generation folks talk about the best way to get more generation is with the generation you already own. Find ways to uprate it, whether it's nuclear, whether it's hydro, whether it's fossil fuels. Look for opportunities to increase the efficiency of those facilities. And that's definitely a part of our overall integrated resource plan.
In fossil fuels, you meant coal?
Yes, sir. All of our fossil
Yeah.
fuels, gas and coal.
Okay.
And Commissioner Tuggle, we do have transmission projects coming up next in the queue.
Right.
And
I'm just trying to deviate my question between this panel and what you guys are supposed to answer or have knowledge of before you hand it off to another team of experts that are there. On transmission, I guess, Mr. Fogg, would be your answer, question or whatever. How about conductors? You know, you see a lot of information available about not having to raise the towers. You can use conductors on the transmission lines and those kind of things. And I've asked the Duke folks in the past, and they kind of, well, you know, that's not really a big item for ROE. A transmission line certainly is more expensive than that. Are we utilizing all of that technology to do what we can to get efficiencies out of the existing transmission lines? Is that a fair question?
It is, and we're exploring options to be able to get those efficiencies. A lot of cases with our traditional upgrades, we're doing traditional methods, but there are advanced conductor technologies that we're looking at and making sure that it's the right fit for us.
Okay. Well, and I don't doubt your answer, but looking at, and this technology's been around for a while, I mean, exploring technology, it's there. I mean, if there's a cheaper way, I would think, you guys would be looking at it for real. And, I would hope you would. I've read a lot on the conductors and, you know, they seem like a viable option in some cases, not all, but I don't hear my Duke folks telling me that they're upfront, doing that. Would you, Mr. Thompson, answer a question about batteries? Is that in your all's forte?
If we could,
Yes, sir.
my concern is our schedule for today, in terms of the presentation of the topics that are before us. If we could try to go ahead and move into transmissions now and then, do things in sequential order, it might be a better time to ask your questions. Some of them may be answered in the presentations that are still forthcoming.
Whatever you think, you're chairing it, that's fine. I'm good with that. I didn't interrupt anybody when they gave me an answer either.
No, I mean, I think your questions are completely legitimate questions that, I think the question is where.
Whatever
are
you
they-
want to do, I'm fine with that. Yes, sir. Go ahead. You
Okay.
do what you want to do. That's fine with
All
me.
right, why don't we go ahead and move forward in the transmission section since there's great interest. Mr. Fogg, I guess you're next in the queue.
Hey, Commissioner. So good afternoon. I'm Bennett Fogg, General Manager of Transmission Engineering. Today, I'll be providing an overview of our transmission projects. I'll provide context on how we identify and evaluate the projects to place them into the multi-year rate plan, as well as context on the benefits for each project. Note that we have 7 distinct projects, and through these projects, we address scopes of work by location for numerous assets. You'll find that these are the same types of project that we deploy for MYRP 1, but that they will be executed at different locations as we continue to penetrate areas of need amongst our vast service territories. These projects focus on areas that we need to continue to address that have a positive impact on the grid. We think about the 7 projects in 4 different areas based on their capabilities. The area of system intelligence allows us to modernize communication capabilities. It gives operators and engineers greater visibility into system events and equipment health, leading to improved grid awareness. The area of hardening and
Thank you.
resiliency strengthens the grid through transmission line and substation upgrades. Transformer and breaker upgrades improve reliability by addressing major assets that are beyond their useful life. And as we dig further into these projects a little bit later, I'll provide more context on what I mean by useful life. And the capacity and customer planning area meets customer obligations as demand grows and ensures that the grid meets compliance requirements. These areas and their capabilities benefit the grid and thus play a critical role in serving our customers. I'll cover additional details on customer benefits and more in depth as I dive into each of the individual programs coming up here. Next, I'd like to cover how we identify and prioritize work, which supports the development of our MYRP portfolio. So we take a systematic, risk-informed approach to evaluating every project. This process starts with the teams that sponsor work, which include both system planning engineers and asset management engineers. System planning engineers are responsible for meeting our compliance obligations and capacity needs. Asset management engineers are responsible for reliability, end-of-life planning, and new technology investments to improve efficiency in the way we operate and maintain the grid. These sponsors take into consideration the following when determining specific locations where work is needed: input from our grid planning models and studies, input from coordination with distribution and generation planners, asset health trending data, reliability trending data, field inspection input from technicians and linemen, and vendor and industry data. We use this information to generate our scopes of work. Now, how do we determine priority? On the graphic here on the right side, you'll see our framework graphic. You'll notice that the various factors around the outer circle are factors that inform the quantitative analysis of the benefits of the work and help us with internal prioritization of project locations.
Yeah, I got this.
These factors help identify scopes that provide the greatest value to customers. These factors also identify scopes that are necessary to comply with regulations, which we prioritize as must-do foundational work. On the next slide, I'll provide more context on quantitative benefits, and we'll review the cost-benefit analysis approach used for MYRP2. Mr. Guyton discussed the cost benefit analysis methodology for distribution, and it's the same concept and principles for transmission. Different inputs, but the same thought process. For transmission, we use the following data inputs to support our analysis of the cost benefit of a project. The condition of the assets associated with the project, including the probability of failure, the consequence of failure, the risk of system overload for certain projects, and the estimated cost of a project based on historical data. Aside from the estimated costs, we use these inputs to help determine the expected financial benefits. As a methodology, the expected financial benefits are based primarily on the benefit from reliability risk reduction, or in other terms, avoided outages. Pairing the input data with the data from the ICE calculator produces benefits assigned as a quantitative dollar value based on the avoided cost of an outage. We run this data through a decision analytics tool that performs a cost benefit analysis, taking the financial benefits monetized over 30 years and the cumulative cost of the project over that same period and presenting it as a benefit cost ratio for each project. All right, so let's start to drill down into the details of the projects. On the left side, you'll see our total planned investment for MRP2 or DEC and DEP, roughly $1 billion in DEC, nearly $900 million in DEP. And for a more detailed breakdown, the cost by overall project as well as by project location is also shown in the filed tech conference materials. Note that costs for the projects vary between regions. And I want to point out that this ties back to our systematic value-based approach. We are intentional about tackling the areas of need, and we let our analysis drive prioritization. On the right-hand side, we demonstrate the improvements we expect for the 4 areas that I referenced earlier. System intelligence gives us smarter devices with improved technology in the form of digital relays and condition-based monitors. Digital relays are capable of providing information to operators on where problems are occurring. Condition-based monitors provide health inputs to grid operators, providing warning in advance of failures. In addition to system intelligence, the hardening and resiliency, or H&R area. This area is broken down into line H&R, substation H&R, and vegetation management. And we group them together because they deliver similar improvements, which is hardening the grid against extreme weather. We also have transformers and breakers, an area that targets end-of-life major assets and proactively replacing them prior to failure, which helps prevent customer outages. And finally, the capacity and customer planning area, which ensures that we meet system compliance obligations and also ensures expanded system capacity for customers as load shifts and is added around the system. All right, so for a deeper dive in each of the 7 projects, as I go along here for each project, I'll give an overview that includes the purpose and a description of the work. And then, as I alluded to earlier, I'll talk more about the customer benefits that the project brings. We also have a section that reflects cost and schedule, and I won't reference these as much, but note that they are found in the filed tech conference materials. So I've mentioned system intelligence a couple times and provided a little context, but what exactly does it mean? Basically, it's our ability to obtain more useful data about the grid and our assets so that we can make decisions in the best interest of reliability for our customers. With the System Intelligence Project, we are modernizing our system protective relays by replacing outdated electromechanical relays with digital relays. We are installing remote control line switches, allowing for quicker sectionalization of transmission lines for fault conditions. We are implementing remote substation asset monitoring, enabling operators to monitor equipment and control substations remotely. Here's an analogy that can help show the impact of system intelligence, particularly remote asset monitoring. So recently I received a notification from my home security system telling me that one of my window sensors had a low battery. The notification came in the form of a triggered alert through the security system app. I also received the notification through email. Not only was I notified of the low battery, but I was also given an estimate of the percentage of battery life left. This intelligence gave me an opportunity to assess the situation and develop a plan to address it, which in this case is a replacement of the battery. One of our system intelligence scopes, condition-based monitoring, or CBM, is designed to provide a similar type of intelligence for our transmission transformers. These transformers are critical assets with a high consequence of failure, including the potential to impact thousands of customers with an outage, as well as produce collateral damage to other substation equipment. We want to avoid these impacts, and CBM devices monitor different elements on these transformers. More specifically, they look for dissolved gases that start to present themselves in the early stages of failure, providing notification if the gases reach a certain level. We process this information through a machine learning platform called our Health and Risk Management System. And this system takes into account many asset health characteristics. And this intelligence allows us to proactively plan for asset replacements. Now, keep this in mind as I'll hit on these analytics again and connect more dots when we get to the transformer project. So what are the benefits of the System Intelligence Program? Mainly, we see improved reliability through reduced outages. For example, modernized protective relays have the ability to provide fault location information. So instead of dispatching crews to patrol an entire line segment, which can be tens of miles, we have data that allows us to direct crews directly to a fault location or very close to it. Additionally, the data better allows operators to isolate that segment remotely with the remote controlled switch to get as many customers back on as soon as possible while the crews investigate the source of the outage. The faster that we're able to address faults, the less time customers are out. System intelligence gives us increased visibility into the system, providing more real-time data and supporting operational efficiency through quicker and more informed decision-making. And I just want to touch on the cost-benefit ratio. You'll see this, and you'll see this as a theme for other projects due to the amount of customers that transmission projects impact. The net financial benefits are demonstrably positive. And beyond that, for this system intelligence project, you'll see a difference in the cost benefit ratio between DEC and DEP, with DEP having a much higher ratio. This is due to the scope of work at a couple of different locations being low cost, but still having a high benefit impact. These locations are driving that BCR higher in DEP. To further illustrate this, let's take a car and let's look at two scenarios that may render the car inoperable. In one scenario, if the front two tires of that car were to blow, then the car will become inoperable. You couldn't drive it. In a different scenario, if the engine blew, you would have the same effect as the first scenario. You couldn't drive the car. You got two different scopes that cause the same failure. However, addressing one scope is much cheaper than the other. The scope to replace the two tires is much cheaper than the scope to replace the engine. You get the same benefit in both cases, a car that continues to operate, but your benefit cost ratio will be much higher for the scenario where it only requires replacing the tires. For the substation hardening and resiliency project, you'll also see a noticeable difference between the DEP and DEC cost benefit ratios, but with that project, it is not as pronounced as it is here with system intelligence. All right, line hardening and resiliency. The focus of line H&R is create a stronger and more resilient grid through the replacement or reinforcement of transmission line assets. This project helps harden the system through cathodic protection, where corrosion prevention devices are installed at the base of tire legs, targeted line strengthening, which includes transmission line rebuilds, replacing wood poles with steel, and replacing degraded lattice towers with upgraded versions designed to the latest standards, and static and overhead ground wire replacements, which provide protection against lightning, and in some cases include fiber optics that support high-speed communication between substations. As you see, we have a diversity of scopes within this project. And I want to note here the tower replacement scope. This scope is applicable to DEP, where there are locations which we are strictly replacing segments of towers for the scope of work. But I want to clarify that we're also replacing towers in DEC, but these replacements are part of the larger scope of line rebuilds, which also encompass different types of line structures for the segments targeted for the scope of work. You can look at the tower replacements as a type of line rebuild. And this is another one of those themes that will show up in another project. work that looks like it's seemingly done in one region, but in each case, the scope is typically part of a broader scope in the other region. Benefits. So again, we have a diversity of scopes within the project. And although line rebuilds and tire replacements make up a large portion of the project, not all assets require a complete replacement. We hit the areas of need, like cathodic protection, where we address just the legs of towers, and overhead ground wire, where only the highest wire on the segment of structures is replaced. This collective strategy improves reliability and resiliency. Hardened assets can better withstand impacts from severe weather or other adverse conditions, leading to the ability to more quickly recover from outages. And newer assets equals less component failures, which equal reduced outages. A couple of highlights from MRP 1. Through Line H&R, we've addressed over 1,600 towers in DEC and nearly 400 towers in DEP. Similar to Line H&R, substation hardening and resiliency creates a stronger and more resilient grid through the replacement or reinforcement of transmission substation assets. This project focuses on replacing both major and ancillary equipment inside of substations, which is executed in the form of reliability upgrades. When we identify a number of critical assets that require replacement at a particular location, we consolidate and coordinate the work. This includes major assets like transformers, breakers, regulators, circuit switchers, as well as ancillary assets such as voltage transformers, surge arresters, insulators, and air brake switches. Consolidating work is critical for creating efficiencies and getting the most out of mobilized resources and associated outages. Typically, many ancillary assets can be addressed during a planned outage intended to address a major asset. Reliability upgrades also give us the opportunity to reconfigure the station, increase spacing, and upgrade to current standards. The sub H&R project also focuses on animal mitigation, which is installing animal-resistant fences around substations to address one of the top drivers of substation-related outages. Benefits of sub H&R. So efficiencies are created with consolidating work, which allows us to take advantage of addressing multiple assets within a single outage window. And it limits the number of times we do work at a location, gaining efficiencies through single mobilization while also creating less exposure for customers. Also, sub H&R improves resiliency. Substations can better withstand impacts from severe weather or other adverse conditions, leading to the ability to more quickly recover from outages. MYRP1 highlights: reliability upgrades at the Atlantic Beach substation in DEP benefit over 5,000 customers. Reliability upgrades at the Mebane Tie station in DEC benefit over 14,000 customers. Similar to what you heard earlier for the distribution system, for the transmission grid, we're also targeting tree removals as a component of our integrated vegetation management plan. We refer to targeted trees as danger trees, and this project focuses on removing these types of trees from outside of the right-of-way. And to reiterate, we define danger trees as trees that are dead, diseased, dying, or leaning towards a line, or any other tree that because of its proximity, shape, type, or size could endanger company assets. The removal of danger trees support minimizing the risk of veg-related interruptions, maintaining adequate conductor to vegetation clearances, formulating a plan to address difficult access areas versus having to address them in an emergent scenario where customers are out, and maintaining compliance with regulatory, environmental, and safety requirements and standards. So here's a little more insight on how we determine danger trees. We utilize aerial scanning technology attached to helicopters and perform flights over all transmission circuits over a periodic basis. The results of the scan creates a tree canopy risk model, which identifies threats, and then we determine if we should act on those threats. Threats are evaluated based on the condition of conductors under max operating conditions. Then models show if a tree can strike a line or if they would grow at a rate to become a threat. Vegetation is typically a leading cause of outages, specifically trees falling into lines from outside the right-of-way. From a benefit standpoint, this project reduces that threat and therefore reduces customer outages. This project also helps reduce impact and damage to the grid during extreme weather events and storms, where we tend to see the most vegetation-related outages. Our work on the Fayetteville-Rockingham 230 kV line serves as the MORP1 highlight. It's a 53-mile transmission line, and based on our tree canopy risk model that identified danger tree threats, we've removed over 13,000 danger trees. Breakers. This project targets replacing degraded substation circuit breakers with breakers that utilize modern advanced gas and vacuum-based technologies. Due to age, wear, and unavailability of replacement parts, breakers are becoming increasingly difficult to maintain and keep functioning per design specifications. The targeted degraded circuit breakers use oil as the insulating medium, which has been identified as a legacy technology. And these designs can no longer be relied upon to consistently and reliably perform their design function. During events, we expect breakers to open to contain the fault to the smallest possible section of the grid. There's a risk that won't happen with degraded breakers. And when breakers do not open as intended, larger sections of the grids are subjected to outages to work around the non-functioning breaker, impacting more customers. We select and prioritize breaker locations based on a number of factors, including field inspections and testing, configuration and redundancy, make model failure trending, and the number of fault operations experienced. Installing modern vacuum and gas breakers, these technologies operate more reliably. At the same time, we're upgrading their controls and communication capabilities to allow remote operation where it doesn't exist, and provide operators more flexibility and control of the grid. There are multiple reliability benefits to replacing legacy circuit breakers. Customer outages due to misoperations are minimized. There's a benefit to the environmental footprint through oil reduction, as oil breakers are replaced with gas and vacuum breakers. And we're able to implement technology that improves communication and remote operation capabilities. Additionally, we avoid catastrophic failures with proactive replacements. These are failures that can cause extended customer outages as well as extensive customer damage. Over the course of their operating life, transformer banks are exposed to a number of stresses that include mechanical, thermal, electrical, chemical. And over time, these stresses lead to a deterioration and degradation of the transformer. The transformer project proactively upgrades transformers, as well as another classification of transformers called voltage regulators. Transformers perform large voltage steps, converting the higher voltages used to transmit power across long distances to lower voltages more suitable for serving customers. And we refer to these as power transformers. We pair the power transformers with voltage regulators. Voltage regulators are a type of transformer that performs smaller voltage steps to fine-tune voltage to the standard range that customers can accept via a load tap changer. There are two different configurations in which we pair power transformers with voltage regulators. In one configuration, the power transformer has a built-in voltage regulator. This configuration is prevalent in DEC. The built-in voltage regulator contains load tap changers with an arc and oil design. This is a vulnerable design, susceptible to catastrophic failure, which can lead to outages and collateral station damage. This project eliminates that vulnerable design. The newer design uses a vacuum load tap changer, which does not create arcing gases as voltage adjustments are made. The other configuration, for transformers that do not have a built-in voltage regulator, they are paired with standalone three-phase voltage regulators. This design is prevalent in DEP. These standalone voltage regulators also have load tap changers that perform the same fine-tuning voltage adjustments as the built-in voltage regulators. Built-in load tap changers. This project replaces the three-phase regulators with regulators that have the enhanced vacuum design, addressing that risk to a catastrophic failure. So I want to take a moment to circle back and connect this project to the System Intelligence Project. While discussing that project, I talked about implementing remote asset monitoring and gave an example. The analytics that we receive from that monitoring play a huge role in helping us determining what I call the sweet spot for transformer replacements. And when I say sweet spot, I mean the moment in time that the transformer has reached the end of its useful life, which is just prior to failure. We're looking to get as much as we can operationally from our assets. Useful life equates to operational life, which is much different than recommended life. The recommended life of a transformer, or the lifespan recommended by the manufacturer, is around 40 years. In most cases, we're extending the life of transformers beyond the recommended life through our maintenance and condition-based programs. Now, when adding the analytics that come with asset monitoring, we get more data on the internals of the transformer in real time, further informing the right time to proactively replace those assets. So again, we're replacing transformers to address a vulnerable design, as well as when our condition-based info and analytics are informing us when it's the right time to avoid catastrophic failure. Benefits of this program. Transformers can directly cause customer outages. It's not uncommon for thousands and even tens of thousands of customers to be served from a single transformer bank. Failures can lead to loading concerns on the grid, making it more difficult for grid operators to maintain required voltage levels. Failures are often catastrophic in nature, with the risk of collateral damage to surrounding equipment and a potential for oil release. Like breakers, the goal here is preventing future failures. We want to identify vulnerabilities and proactively replace these assets before they fail and result in operational challenges, and increase potential for long duration outages. When transformers fail, they are typically one of the top 5 leading causes of customer minutes interrupted. Ultimately, this project improves system reliability and resiliency by reducing the risk of disruptive outages from catastrophic equipment failures and mitigation of the impacts and costs associated with an unplanned failure. Highlights from MRP1. Transformer bank replacement at Arrowwood Retail Station in DEC benefited nearly 3,000 customers. And a transformer bank replacement at Havelock Substation in DEP benefited about 3,500 customers. The last project I will highlight today is capacity and customer planning. This type of work is critical to meeting capacity needs of our growing and shifting customer base, and is critical to adding new customer connections. Scopes within this project help to expand the grid while ensuring that adequate power flows are maintained. The capacity and customer planning project is also critical to meet our compliance obligation under NERC standards. Standards developed by NERC are often developed based on past grid events, with the intent to keep those type of events from happening again. Specifically, this involves upgrading transmission equipment such as transformers, breakers, switches, and conductors to higher capabilities and capacities, as well as enhancing the associated protective relay schemes with redundancy. Ultimately, this project aims to ensure grid stability to maintain a healthy grid and prevent widespread blackouts. Benefits of the capacity and customer planning project: meets federal compliance mandates for grid reliability, maintains grid reliability and stability, and provides capacity upgrades and new customer connections to serve customer needs. So that concludes the transmission portion of the presentation. And with that, I'll take any questions you have.
All right, I have a few questions from commission staff, and then we'll go to other questions from commissioners. Commission staff had some questions specifically targeted toward the completion of transmission projects. Could you provide me with the percentage of transmission projects from the initial multi-year rate plan that have been completed on time and on budget?
So I don't have MRP1 data in front of me
Okay.
to share, but we do file those reports quarterly and annually that would have that information.
Could you compile that information and share it with us after today?
Absolutely.
All right. And these other questions would kind of go towards some of those same issues. It related to what percentage of transmission projects from the multi-year rate plan are at or below their projected spend. And likewise, what percentage of those projects from the initial multi-year rate plan are incomplete compared to where they were projected to be completed and what milestone you've actually reached. So if you could follow up and provide us with that information after today, that would be appreciated.
Will do.
If you could walk me through the analysis or modeling that Duke utilizes to prioritize and select transmission projects to include in a multi-year rate plan, and what criteria Duke is using to select those projects. So if you can help me with that, that would be appreciated.
So we have sponsors of projects, our system planning engineers and asset management engineers. And from a system planning perspective, they select projects based on standards that we need to meet for the grid, as well as projects that would facilitate new customer growth based on our obligation there. From an asset management standpoint, this is more of the traditional method that we've seen. We utilize condition-based data and trending data to understand the areas that we need to make improvements on to continue to reliably serve our customers. So those sponsors take projects and they put them through our decision analytics tool, or help to score them and put them through our decision analytics tool. And then we can determine the value of the projects and the value of greatest need to the customers. And then we'll use that information to help determine how to prioritize projects.
Now, that is the process you're using now. Is that different at all from what was used with the last multi-year rate plan, or is it the same?
Same process.
Same process. So there've been no deviations that you're aware of?
Not that I'm aware of. Outside of part of that process is pairing the input data with the ICE calculator. And we have a more updated version of the ICE calculator. I believe we talked about that a little bit earlier. So those inputs are more refined there in terms of specific data to Duke Energy customers.
So I believe that was the ICE 2.0. Is that
Correct.
correct?
That's correct.
The one that was most recently released back in March of 25?
Correct.
Okay. Now, can you tell me a little bit more about impact modeling? And I believe that was on slide 34. And how Duke uses that to select projects in its prioritization framework. So impact modeling itself, how does that work back into the prioritization scheme?
Impact modeling. So I'll talk a little bit about this framework here.
Okay.
Again, I talked a little bit earlier about our sponsors and the data that they receive as inputs to help make decisions on essentially what work we need to go after. And when you look at the framework here, those are different considerations that go into that. Compliance, you'll see upper left in the yellow, compliance with regulations. So that's an input that we'll need to take into the account to help determine the type of projects that from a planning standpoint we'll need to pursue. Reliability and integrity of the grid is another example, which is the green, first green highlight on the right. That is the condition of our assets and what's impacting our system, and looking at the data that we've seen from recent events and trending that data and really getting after and finding the cause of that and formulating a plan to develop system reliability programs to approach that so that we can go forward and produce projects and detailed projects to be able to address that and continue to serve the grid reliably.
All right. Now, Duke outlines its project planning approach that begins with kind of a circuit level analysis, and then it takes into account practical constraints and the sequence of work at individual substations. How is this approach different than the project planning approach for transmission projects?
If I've gotten your question right, I believe you describe sort of the life cycle of a project where we
Yeah, and I think initially what we're looking at, that approach that's taken into account for, say, individual substations,
Mhm.
and comparing it to what you would do more generally for transmission projects.
Ask your question one more time.
All right, I will.
Sorry.
And I'm going to, Duke outlines its project planning approach that begins with circuit level analysis and takes into account practical constraints and the sequence of work at individual substations. How is this approach different from the project planning approach for transmission projects?
If I could, so,
Okay.
excuse me.
And of course, I will be candid, this is not one that I authored.
Oh, that's
So
fine.
if I have misstated it in some way, I apologize for that, but I'm reading it verbatim as I see it.
Yes, sir. So Commissioner, what you've described there, I believe, is what I described from a distribution planning perspective. We do a circuit level analysis and then up to the substation level.
Mhm.
Mr. Fogg can provide more detail, but that's the different levels or segmentation of the distribution system. Circuit level is a lower level. Circuits are all associated with the substation. So that's how we build our projects up. I suspect that, and Mr. Fogg can add to this, is when they're looking at particular projects, whether it be transformer upgrades, et cetera, they have a population of transformers that they review and look at. And then whichever ones they select would roll up to be under that project. But I'll let you confirm that. But the distribution was what you were describing in the question.
That is correct. And I will say our staff is much more nuanced in detail in understanding some of these individual dynamics.
And to add to that, we do have a process where, we have a set of assets that we're looking to replace, upgrade. And as a part of our process, in the development phase, we'll make sure that we're looking at some of the issues or the projects details, project locations that, we would get from distribution that Witness Guyton just described. And we're gonna make sure we're consolidating that work and planning the work around ensuring that we're minimizing the impact in terms of outage coordination. So that's one of the ways we're really trying to consolidate work.
Okay, and how do transmission planning and distribution planning processes interact, if at all?
So I'll start if you don't mind. So, certainly from a distribution planning perspective in capacity particularly, we're looking at identifying potential or identified predicted thermal overloads on the distribution parts of the system. So that'd be the circuits outside of substations, but also that information is rolled up to the substation, the power transformer level that Mr. Fogg described. Our distribution planners, if we see a predicted overload on a power transformer or a bank in a substation, we put that project together from a scope standpoint and hand that off to transmission because they actually engineer and execute or inside the substation fence. So in that case, transmission kind of becomes our general contractor. We're the owner. We've identified an issue. We prescribe some work we want them to do, but they've got the expertise to work inside the substation fence and do those kind of projects. So that's when we hand off to that. How that links into transmission planning, you may have to describe that part.
Yeah, and specific to that, once we understand the capacity needed, then we'll have our planning folks run studies to understand what impact there is on the electric grid. And if there are any other necessary upgrades that we need to have on the grid to be able to support that additional capacity.
Very good. I think that frames it in a context that makes a lot of sense. Can you speak to the process of how Duke identifies and prioritizes transmission projects that replace legacy technologies and or corroded wooden structures?
So when I think of corroded wooden structure, I'm thinking of our wood pole replacement. So we have an inspection program that analyzes wood poles. And so when we find that those wood poles need to be replaced, we'll set up a program to replace those. The first part of your question, could you repeat that?
The first part dealt with replacement of legacy technologies.
So when I think of legacy technologies, I'm thinking of an example with our system intelligence program of electromechanical relays. Those relays are near their end of life. In some cases, they're no longer supported by the original manufacturers. We're not able to find replacements for them. So we have to find a new alternative for them, which are typically digital relays. I talked about that a little bit earlier with system intelligence, but we also get a different element from that in terms of reliability. We're able to, from digital relays, get the ability to pinpoint data or pinpoint fault locations a lot earlier. So that gives us another benefit in terms of being able to find and address abnormal conditions on a system much quicker, which ultimately leads to reduced outages.
And improve reliability.
Correct.
Okay. Now, during the 2022 multi-year rate plan DEC technical conference, the presenter on the transmission projects stated that Duke sees 50 to 100 sustained faults on the transmission system per year. Is that still accurate?
I have not seen the latest number of faults that we've sustained faults total that we've seen on the Duke system. But it does sound in the ballpark.
And do you have any idea how many momentary faults, and I guess that's sub 1 minute faults, the transmission sees per year?
Right. On transmission grid, momentary faults are faults less than a minute, and I don't have that information.
You don't have that? All right. And why do some of the transmission projects only include capital costs while others include capital and O&M costs?
The transmission projects that include O&M cost are a couple of different, fall into a couple of different categories. The first category is net new station or net new line. That would be incremental O&M that comes along with that. The other category would be more particular to type of work, type of scope with pole replacements.
I see.
We are replacing the poles. The poles themselves are the new assets, but the wires, the conductors are not. So there is an O&M cost associated with transferring those wires from the old poles to the new poles.
So it's not necessarily related to longer installation timelines,
Not that I'm aware of.
not based upon your explanation, okay? In the explanation of need of capacity and customer planning, Duke mentions that these projects support connections for new transmission delivery points. What types of customers are you interconnecting? For example, industrial, data centers, or what would that entail?
It could be retail, it could be industrial, it could be commercial. What it's not are data centers.
What it is not is
It
data
is
center.
not correct.
Very good. Now, it appears that some of the capacity and customer planning projects are driven by a recent update to NERC standard TPL 001. Can you speak generally as to which of the transmission projects proposed are largely for compliance with NERC standards and which go beyond NERC standards?
So I'll repeat that, if you don't mind repeating that question.
Sure. It appears that some of the capacity and customer planning projects are driven by a recent update of NERC standard TPL 001. Can you speak generally as to which of the transmission projects proposed are largely for compliance with NERC standards and which go beyond NERC standards?
So in terms of compliance NERC standards, specifically the TPL 001, these projects are projects where we need to, we have to meet compliance with redundant protection along the associated with those stations and lines. So those are the projects that are included in that scope. I don't have the specific scope for each of those projects laid out here, but I don't, beyond that, there are other reasons that our planning team coordinates the projects beyond just the protection. It could be the upgrades needed for capacity. We're seeing a capacity, so that's not necessarily related to TPL1, which is the redundancy piece of it. It's just the capacity is needed in the area because of customer connections.
All right, thank you. Let me see if there are other commissioner questions. Chair Brawley? From the other commissioners here? I'm not seeing any from Commissioner. Okay, Commissioner Gaida, go right ahead.
Thank you. Thank you, Commissioner. I'm thinking about, I apologize, Mr. Fogg, this is a multi-part question, but it's not too bad. I'm thinking about lead times for large transformers and breakers. Can you characterize a little bit how these are impacting your your project costs, your strategies around design standardization and inventory levels?
Yeah, we have been impacted from breakers and other components, those manufacturers expressing longer lead times. And so to work around that, we have tried to engage supply chain a little bit earlier in our process, in our process, to make sure that we can get a good grasp on what the lead time is, as well as discuss any alternatives if necessary, to work around that.
Just a quick follow-up. So it's not necessarily, so you're really tackling this at the project level and with your suppliers. Is it impacting things from a cost perspective at the inventory level? Like, are you finding that you're having to maybe add spare equipment to your inventory so that you can just stay ahead of projects? And I didn't know if that was part of the equation.
Yeah, I'm not as involved in that piece of it, but there have been cases where we are looking at alternatives. So I would imagine that there would be some type of cost of bringing in a different type of alternative breaker and storing it.
Okay.
But I'm not aware specifically of what those costs would be.
Okay, thank you.
Commissioner Tucker.
Gentlemen, you have in here in your presentation all kinds of numbers with benefit cost ratio, et cetera. Can you tell me total how much money we're proposed spending about? Is it 2028? Is that correct?
End of 2028, yes.
Scott, how much money are we on transmission and distribution are you planning to spend if you could get all the equipment, if all the stars lined up correctly? What is the total of what you've presented to us today?
So for transmission, in DEC, we're looking to spend about $1 billion. And in DEP, we're looking to spend roughly $900 million.
Okay.
And, excuse me, and for distribution on slides 9 and 10 in the presentation,
Okay.
the stacked bar graph on the far left of the page, at the top of the bar graph, you'll see the totals, Commissioner. So on page 9 is DEC. And for those distribution investments, it's 1.6 billion. And then on slide 10, that's the DEP version of that slide.
1.2?
One point, for DEC, it's 1.6, for DEP, it's 1.4. On slide 9, the bar graph to the right is just a breakdown for substation and line. So page 9 is completely DEC, but the total is 1.6. That 1.2 you see there is a subset of that 1.6.
Okay, so you're spending 1.6, is it?
1.6 in DEC and 1.4 in DEP.
Okay. So that's 3. So you're going to spend roughly $4.9 billion in the next 2 years?
That's what we will place in service. Those are in service dollars.
Okay. All right. That's fine. Just humor me a minute, if you would, gentlemen. We don't have ultimate approval on the transmission lines, do we? That's by another group, the Carolina Transmission Group.
So I can speak to that, Commissioner Tucker.
Yes, sir.
The Carolinas Transmission Planning Collaborative.
Yes, sir. Is your mic on?
Yes, sir, it is.
Okay,
I'll
all
maybe
right.
speak a little louder. So it's the Carolinas Transmission Planning Collaborative. I can't think of the acronym, but it follows
Right.
that string.
Close enough.
That is a regional transmission
Right.
focus group that's really looking at the current state and the future state of the transmission system in North and South Carolina. And they're really focused on reliability needs and then projects that address those reliability needs. They are not really an approval kind of process. They're more of a validation type of process. And we use them for the red zone projects. We've submitted all of our red zone projects to date through that process to validate, one, the need and validating the congestion and constraints we've identified. And then also looking at the solution, the action that mitigates the congestion and constraints.
Well, thank you, sir, for that. I guess that's what I'm referring to. In the red zone projects, you didn't need the commission's approval to go ahead with those transmission projects as long as you got the Carolina Transmission Group approval. Is that not correct?
No, sir, we'll need, that's why we're bringing those costs to the commission. We do that under your oversight.
Do you recall that Duke requested of the commission a letter of agreement of some sort before they went before the Carolina Transmission Group? Well, what I'm getting at, we don't ultimately, I guess we certainly regulate you, but as far as the red zone projects or some transmission, you bring it through the commission, not anything otherwise, but then you don't need our approval. You go to that group and get an approval. Is that not correct?
No, sir, we don't get an approval from them. We get an endorsement. The cost associated with the red zone projects in DEP and DC are included in MYRP 2.0.
Well, Mr. Holman, there was I know I was one of them that was not in favor of the red zone projects, but I guess it got approved by the commission. Is that what you're saying? And then it goes to the Carolina Transmission Group?
I was not involved in
Yeah.
the first MYRP 1.0.
Okay,
When the original carbon plan was done, I believe CPRP, I should say, there were, as I'm thinking, 13 or so red zone projects
Mhm.
that were approved by the commission at that time. In the last order that was entered, the discussion amounted to going to the Carolina Transmission Planning Collaborative and having them chime in on the various projects that were proposed as part of Red Zone 2.0.
Yes, sir.
And of course, they've adopted this multi-value strategic transmission process for evaluating the projects that come before them. And you will be dealing with red zone projects a little further
Yes, sir.
in the presentation cycle.
Yes, sir. That's correct.
okay,
So that will be coming up shortly.
okay. Two more questions, if I may.
Sure, go right ahead, sir.
Who answers about battery storage? I know Mr. Thompson's here. Would you be the individual? I don't know which one to ask. Distribution, transmission, Mr. Holman, Mr. Thompson, which one? Do I ask you, sir?
Commissioner Tuck, I'm sure my colleagues in the back will be happy to hear that. I will respond to any questions about battery storage.
I'm sure they
He is
would.
Next in
If
the
I-
queue.
If I may caveat, yeah, I do have a last section, and that I'm here today to speak.
Well, just put them out on a limb if you want to. I hear, I was in Washington about 100-hour batteries. And my question to you is, we have tons of solar without battery storage or without optimal battery storage to be of any kind of impact, such as with Winter Storm Fern or Elliott or whichever, an event. Are those batteries coming online? Are they viable? Are they priced where you could put a group of them together? I've seen some in different areas. And of course, Commissioner McKissick talked about some places that he was aware of that they had a cluster of batteries that were in storage. How long does that storage last? And can you charge a battery in August and then tap the energy in February, 6 months later or something like that to help us in the winter? Because, the beef against solar is they don't help us much on dark days because the sun's not shining. Help me with that, and where are you with that as far as advancing thoughts on that technology? And is any of those, any expenditures in here involve anything that's related to, long duration battery storage? Is that fair? Did I ask it correctly?
And I think he's thinking about the Forum battery, the iron battery that's been
Right.
discussed by Forum.
Hopefully I can give a response that's somewhat informative and enlightening. And I did not come today prepared to talk too much about Forum. You will have the pleasure of talking to me in a few months when we come back for the integrated research.
That's fine if you
plan.
want to do it then.
On there. I'd like to at least try to give you the first level of detail, and the specific answer to your question, no, none of our investments bring in today are going to be the 100-hour duration Form technology, which is iron air chemical reaction storage. In general, I think the question was about readiness. This was the second part of your question, readiness. No, we do not see iron air projects as ready for investments to come and solve the grid challenges we know today and ready to put forward the commission and the rest of the intervenor scrutiny to stand up to the backbone of projects for us. So the answer is no, we are not bringing them in today's technical conference or MYRP2. And they might be several years even after that before we're ready to deploy and bring forth in full scale to the large sizes that are being discussed.
So you got a projected, how far off is that? Technology availability of batteries and the expenditure.
Yeah, I'll hazard to go one level of detail on that. Best I feel confident responding to you, Commissioner Tucker, is that I am aware of other utilities in the country piloting form and deploying those so that the industry and our utility included can get helpful and representative data so that they can be modeled and potentially then
Okay.
included as in part of our plans, including the T&D material today.
Okay, so
in
that's,
some
it's still a ways off then.
Yes, sir.
I'm just keep thinking about, we were talking about it at lunch, about how much solar we've got in North Carolina. If we could, put batteries around it and get storage there and have electrons stored there, it would be a good thing in the wintertime. And I don't know if Mr. Guyton or Mr. Fogg will answer this, or Mr. Holman, but explain to me what happens when you lift a tower. Does that enhance quality? Does that enhance capacity? I see stories about tower lifting, and when you talked about, you showed a bunch of towers in here, Mr. Fogg, I think in your presentation. By the way, the conductors were in your presentation under that bottom line there. What does that do for the system?
In some cases, it helps with capacity, lifting those towers to be able to minimize the sag that we see. So I think that's a lot of cases that's the route to go.
So you're talking about when the lines go like this, you lose transmission ability? Is that what I understand?
No, you don't lose transmission ability, but you start to get into situations where you encroach on other lines or other components. So you want to reduce that ability there. Because
Okay.
if the line hits something else, it'll create an outage.
Right. And you guys enlightened me today. I didn't realize how much animal interference was involved in as much as a 30-06 bullet. I mean, a possum going in on a substation, with fencing and those kind of things that were there. And then you have something on the line called Wildlife Guard. Is that what we're talking about? What does that do?
So we have that in distribution, transmission, version, but there was a.
So that's your question.
So
Yes, sir.
I'll be happy to take it.
Yeah,
It's something
yeah,
in
okay.
Transmission.
Yes,
So-
sir.
So there was when I talked about equipment retrofit, and I can point you to the slide, there's a picture
I saw it.
of a transformer installation where the bushings come out of the top of the transformer, and then the lead wires go up to the primary. Historically, that was energized at whatever the primary voltage is, 12,000 volts, 7,200 volts. The Wildlife Guard actually provides an insulation down onto the bushing and up the wire. So if a squirrel or bird is on top of the transformer, their ability to actually make contact and create a fault, we've mitigated. I won't say we've completely eliminated, but the intent is to insulate that where that doesn't cause a fault anymore.
Okay. Yeah. Well, thank you for that. I appreciate it, gentlemen. Thank you. Thank you.
All right. Thank you.
Commissioner McKissick.
Yes, and I think we've concluded with that portion of the presentation. I think the next issue that we're taking up is grid planning and integration. Mr. Holman. And I thank you for indulging us in answering a variety of the questions.
My pleasure. So good afternoon, Presiding Commissioner McKissick, Chair Brawley, Commissioners Tucker and Gaida. My name's Sam Holman. I'm on the Duke Energy Grid Planning and Integration Team. It's called the GPI team. My specific focus today will really be in two areas. One would be the red zone expansion plan projects, referred to as RZEP. That's the acronym we use. And the network upgrade projects associated with Duke owned and operated generation assets. As you know, we use many and sometimes confusing acronyms in our industry. So for today, I'm gonna take a pledge of acronym abstinence. If I use an acronym that I do not explain, please stop me and ask me to clarify.
You may not have wanted to say that.
I'll give it a shot, Commissioner McKissick. So in my colleague Brent Guyton's comments, introductory comments, he used the word foundation. And I think that in today's world where we're at, that's a very important and meaningful word. Having a common set of working definitions on the important topics of the day, I think is critical to our collective success. And so what I'm going to try to do in these couple of slides is give some working definitions and structure around what a red zone project looks like, the red zone expansion plan project, and really what the red zone are, I guess, and what the projects are, because there's a difference between the red zone and the red zone projects. And also words like network upgrades. So red zone projects, and did I advance the slides correctly? Did not. Yeah, I did. I apologize for this. Am I going the right direction? Yeah. Here we go, almost there, I believe. There we go. So the right-hand part of this slide kind of describes what these red zone projects look like in the terms of execution. They're very similar to the work that my colleague Bennett Fogg mentioned. They're equipment replacement type projects. As a working definition, here's what I'd offer. They're transmission projects, and that's the key word, transmission projects, that are proactively and strategically conducted to address congestion and constraints that have been identified through a wide set of studies that we're obligated to do in our various roles at Duke Energy. So we've mentioned several times the Carolinas Integrated Resource Plan. That's one of the drivers for the red zone effort. It identifies the generation we see interconnecting or needed over a 15-year window, but in the MYRP process, we're looking out 2 of those 15 years. Brent Guyton mentioned the fact, and I think Commissioner Tucker, you mentioned the fact that the population in North Carolina is growing. I looked at the latest statistics where North Carolina's been the easiest state to do business in for several years in a row. It's also, depending on what you look at, in the top 5, worst case top 10 in percentage population growth. If you look at the Carolinas combined, it's one of the top population growth areas in the country. So we've got to plan for that. We've got to plan for that. Mr. Guyton mentioned the kind of peaks we've been seeing for non-historic temperatures. That's an important data point. We're seeing all-time peak loads in the Carolinas, DEC specifically, for non-historic peak loads. And then, so we've got to plan for that. In addition to that, we mentioned earlier the transmission planning standards that NERC holds us accountable to as a transmission planning registered entity. We do reliability studies, looking at voltage, looking at thermal issues, and we identify the need for transmission work. So those 3 sets of studies present the opportunities that the red zone mitigates. And we'll talk about that in a minute. So it supports a broad array of a broad value proposition, from generation additions to customer growth and expansion to reliability studies that we're obligated to perform under our NERC responsibilities. The term red zone is a Duke created term. Our subject matter experts in transmission planning, I think my colleague Bennett Fogg mentioned that process. They were looking at these pockets, these zones of congestion that continue to show up in generation interconnection studies, in customer growth analysis, in these reliability studies under the TPL standards, and they just simply used red to denote those zones. And you'll see these red zones in a minute in both DEP and DEC. We've been a national leader in this kind of zonal concept. We've worked with other large utilities, our peer utilities, in kind of building that kind of concept out, where you're looking at multiple causes of congestion and constraints in a particular zone. What's the most cost-effective, the most efficient way to mitigate that congestion and that constraint? Now, network upgrades, on the other hand, is a FERC term, Federal Energy Regulatory Commission term. And it's from the Pro Forma Open Access Transmission Tariff. The O is the acronym for that. And they're similar to red zone in concept. And as a matter of fact, our early work with network upgrades kind of drove us towards the red zone concept. In the past, we were in a serial or a sequential type queue process. But they're transmission improvements that allow us to integrate new generation assets to the North Carolina grid in a reliable and a secure fashion. We're obligated to do that, both in our obligation to serve our customers in North Carolina and our obligation not to negatively impact the broader Eastern interconnection reliability. So they mitigate congestions and constraints associated with generations additions. Now, for this particular information in this particular rate case, we are only talking about Duke Energy owned and operated generation. We are not talking about third-party generation owner operators. This is just the generation additions that have come through the integrated resource plan process. And it's similar work. Like I said, they're very closely related to red zone. It's equipment replacement, it's equipment enhancing, it's transformers, it's lines, it's breakers, it's terminal equipment. It's basically work that will allow us to transmit more electricity over that particular piece of equipment or that series of equipment. The information on the left kind of gives you a cost or investment perspective on the two programs. As you can see from a network upgrade perspective, they're very similar in DEP and DEC. But if you compare the red zones, DEP to DEC, you will see a larger investment in DEP red zone. And that's because of the nature of the work. The complexity and the scope of the work needed to mitigate or address the congestion in the DEP red zones requires that degree of investment. Summary point on this slide here is that if we're going to successfully implement our Carolinas Integrated Resource Plan, successfully manage the customer growth we're seeing in North Carolina, and maintain and keep up with the reliability requirements we have under NERC TPL standards, we have to get this work done. The red zone projects and the network upgrade projects. So how do we identify these projects? That's been a common question from the commissioners today. How do you recognize, how do you identify the needs that come out of the red zone projects and the network upgrades? Well, the first one is we use and this is a mouthful, the Definitive Interconnection System Impact Study, or DISIS. And that's a fancy name for our cluster study approach. And we're a leader in the industry in developing that concept as well. We've worked with companies like Southern Company, PJM, MISO to enhance that overall process. It's been a really important development for us in terms of how we study these approaches. It identifies those handful of significant projects that cut across multiple generation interconnection projects that continue to show up when we look at customer growth and customer expansion, and continue to show up as we do our NERC directed and required reliability studies. And the goal here, one of the goals here is hopefully bundling or looking at this from a cluster perspective will reduce the number of generator interconnectors who are pulling out of the queue. If you talk to generator operators and generation service providers across the country, when generator interconnectors pull out of the queue, it creates all sorts of churns and delay. And nobody is served for delaying the interconnection process. All you have to do is read some of the conversation at a national level, at a NERC level. We've got to figure out ways to interconnect generation faster without compromising reliability. That's the trick. How do you do that? And we believe the red zone approach helps us to avoid those generator interconnectors from pulling out of the queue. Then, as we talked about earlier, we validate it through a third-party organization, the Carolinas Transmission Planning Collaborative. We take our red zone projects to them. They look at it from a need. Do they agree with the congestion and the constraints that we've identified through our studies? And do they agree with our solutions, our mitigation approaches? And to date, we've taken all of our red zone projects to them, and they have endorsed it. They don't approve, but they do endorse. And these are subject matter experts from stakeholder groups across the Carolinas, North and South Carolina. They're our neighbors in a lot of cases, very, very well-versed in this space. But we think that's an important step for the validation observation piece of this. I'll give you an illustration that I thought of and as we were thinking about these red zone projects. So I live in a small town, and over the last 5 to 10 years, the population of our small town has grown in an accelerated manner. Folks are building houses, they're building apartments, they're building condominiums all over the place. Our little town's expanding horizontally and vertically. And as you can imagine, and maybe as you have experienced in your situation, the roads have not kept up. The roads just simply cannot keep up. By the time they're built, they're too little, and it always seems to be they're too little, too late. And that creates congestion and constraints and frustrations in our little community. It's kind of like the road system, the transportation system is the long pole in the tent for our community as we experience this population growth in our little town. So from the electrical side, red zone is our process for managing this and getting in front of the needs of our reliability commitment to the Eastern Interconnection and our obligation to serve our customers in North Carolina. I kind of wish we had a strategic, prudently proactive strategy for roads in the town that I live in. Maybe that'll come in a future state, but it's not the case right now. So flipping over to network upgrades, they're identified through similar processes, the DICES studies, the network, the studies that we analyze, the thermal voltage constraints that are N-1, 2, and 3 constraints that changes to the grid create. The difference is they're generally targeted towards specific generation assets owned by Duke in this case. We cannot connect these generation assets without these network upgrades. If we did, we would be diminishing the reliability of the grid in North Carolina. And it's really important in the eyes of a system operator to have the generation added with the network upgrades complete. Because with that combination, we can count those generation assets as capacity and as designated network resources. That means the grid has been built to accommodate those generation assets. That's really important on days like Winter Storm Fern, Winter Storm Elliott, and hot weather we saw last summer. We're obligated under law, federal law, to complete these network upgrade projects to support the generation additions that come through our interconnection process. So it's all about reliability. And it's a key point is what Brent Guyton mentioned earlier, and that is the planning aspect of this. You generally discover the need through planning processes. And the focus is you plan it, you discover the need, and then you execute the solution to what you've discovered. There's a phrase we often use, and I've used it here in front of this commission. You plan to operate so that you can operate to the plan. So your operators are not put in an unplanned for state. That's not a good situation for an operator. I've been around operators for 40 some odd years. And it's never a good situation to put them in an unplanned for state. So the real challenge is you've got to have these network upgrades so that you can interconnect this capacity and designated resource generation assets. It's never a good idea to use the grid as a laboratory. And when you interconnect generation and don't complete the network upgrades, you're pretty much experimenting with the grid. And again, in my going on 41 years in June in the industry, mainly in operations and planning, that's never a good idea. So let's dig a little bit into red zone projects. So there's the red zone. I'm halfway colorblind, so I'm trusting everybody that's red. I think it is. That's what Bennett confirmed, that it's red. But here's the subtle point on red zone. So the red zone are the pockets of congestion and constraints that we've identified through that broad set of studies that we perform, from the CPIRP study, or the Carolina's Integrated Resource Plan studies, to the NERC required studies and the customer growth studies. The red zone projects are the mitigation for that congestion. And it's the red zone projects we're bringing to you in the technical conference and then later in the hearing for approval. The bottom line here, these red zone projects position us to be prudently proactive and avoid negatively impacting reliability for our customers in North Carolina. You've probably heard this before, but operational excellence is central to all we do at Duke Energy. We've got a accountability framework that says you plan, you do, you check, and you adjust. And I think as we move forward, it's going to be vital that we're really close together between Duke and the commission on a lot of the independent variables that we don't control. We don't control who's going to move to the state. We don't control the weather. We don't control a new technology that may come up 5 years from now. So I'm very encouraged through the IRP process and the MYRP process of the close-in collaboration that's required by the update cycles. The IRP, the Integrated Resource Plan, looks out 15 years. We're going to be updating that thing every couple of years. We're going to be in front of you with, okay, what's changed? We're checking and adjusting. Help us do that under your oversight. The multi-year rate plan, same way, every 2 years. We're going to be checking with you. If things change, we'll collaborate on those changed. The point here is that we want our grid to be ready for whatever generation technology comes up over time, because that's the point. There's no perfect singular generation technology. We cannot put all our eggs in one basket. That's not a good thing for anybody, and it's certainly not a good thing for operators. What we need is more than just megawatts and megawatt hours. That gets a lot of attention because that's what we post peaks in and energy consumption in. But what about inertia? Getting more attention these days. What about ramping? What about regulating? The ability to be flexible. What about voltage support, both dynamic and static in terms of megabars? Really complex concepts, by the way. And an emerging issue is system damping. How stiff is the system? How much of a punch can our system take and stay in the fight? So we need all those capabilities. I've mentioned this before in front of the commission. They're essential reliability services. There's those services that a healthy and reliable grid has to have. So we've got to be smart enough and strategic enough to position the grid in North Carolina to be cost effective to our customers, be reliable to our customers, and to be supportive of the broader Eastern interconnection. So if you look at the slide here, it's got the projections on the cost on the right. You'll notice for the red zones, the DEP, North Carolina costs are much higher than the DEC, and that's because of the nature, the scope, and the complexity of the projects to address the congestion and constraints in DEP. And the time frame fits the MYRP schedule. So let's look a little deeper. We've got similar slides to what Mr. Guyton and Mr. Fogg had in terms of benefit cost ratio. Those are solid benefit cost ratios. Remember, these are transmission projects, so they touch a lot of customers. Bottom line here is that we're trying to be prudently proactive for the changes that we see coming to our grid, not over 15 years, but really over 2. And as you probably know, when you're looking at independent variables, you've got a much better chance of getting things roughly right in short term than you would into the extreme long term. The analogy I'd use there is weather. You may trust the weather for tomorrow. Are you going to trust the weather 2 months from now? Probably not. So another reference here I think is really important, and I think Mr. Guyton mentioned this earlier, House Bill 951, and I'll quote that I think is really wise counsel for all of us here: to ensure that any generation resource changes maintain or improve upon the adequacy and reliability of the existing grid. I think that's an outstanding statement. If you look at the nouns and the verbs in that statement, it's any change on the noun side and it's ongoing on the verb side. So this is a commitment that we're making with the oversight of the commission to our customers in North Carolina and to the broader Eastern interconnection. Our obligation is to serve our customers in a reliable yet cost-effective manner and not burden the broader Eastern interconnection. So a couple of the facts here that you've probably seen: over 8,000 megawatts of generation depend on, and DP and DEC depend on these RZEP2 IDO projects. We've completed 5 of MYRP1 projects in red zone space. I think there's 4 in DEP and 1 in DEC. And so we're on our way. Network upgrades now, you'll see the cost comparison there. They're comparable across DEP and DEC. This is all about integrating generation assets reliably, and it's our generation assets that we'll own and operate. We use similar technology and study capabilities that we use in red zones, the DICES studies, the reliability studies, N-1, N-2, N-3 analysis is dictated by NERC standards. If you look at the picture down there, that's our Monroe Energy Storage Site in North Carolina. You see all the transmission that surrounds it. That's what interconnects that generation asset or that energy storage asset to the broader grid. And just for your information, this particular facility, energy from this facility helped us during the two storms in late January and early February. And I can promise you, every megawatt and megawatt hour counted for those many days when it was as cold and snowy as it was. Few of the benefits of network upgrades, and I'm approaching the closing here. This is all about resource adequacy, which the integrated resource plan focuses on that. Cost-effective resource adequacy. Are we ready for what's coming at us, not just tomorrow, but out 15 years with a lot more certainty over the next 2 years? If you look at that highlights down at the bottom, we're not alone in this challenge. Everybody is seeing a lot of interconnection requests coming through their queue. Most of the large transmission service providers have gone to a cluster approach. So there's fewer generation interconnectors dropping out of the queue, which is a good thing for everybody. And so this is a national challenge. It's how to get speed to the interconnection process without compromising reliability. So in closing, I'd offer this. So why is this all important? Why are we sitting in front of you today going over red zone projects and network upgrades? You know, why is managing interconnections, managing our customer growth, managing our reliability responsibility under NERC important? Well, it's two really simple things. It's our obligation to serve our customers in North Carolina, our regulatory compact that's existed for well over 100 years. And on the broader perspective, it's our obligation to support Eastern interconnection reliability. It's our obligation to comply. And you wrap all that up in the fact that we're talking about the largest machine, the Eastern interconnection, that humans have ever made. Now, there are people in the industry that will argue with me, we're really not the largest, but I can almost promise you it's in the top 2 or 3. And if you look at the age of the Eastern interconnection in terms of size, it was large before the other ones. And so it's the most complex machine humans have ever made. It's also the most critical of the critical infrastructures, not just in North Carolina, not just in our country, but in the world. Everybody depends on it 24/7 by 365 all the time. And I'd offer to you, if you want some evidence of that, check out the reports that are going to be coming out over the next couple of months on the Iberian Peninsula event that happened last April in that part of Spain and Portugal. Nothing good happens if we're not diligent, disciplined, intentional, and methodical. We're not serving our customers adequately if we fall short on anything like that. Our customers depend on us to do this 24/7 by 365. And Duke Energy is singularly responsible and accountable for reliability and security in North Carolina to our customers, to you, the commission, and to NERC. We've got to carry this responsibility out. We got to carry it out correctly. So before I turn it over to my colleague, Gray Thompson, and any questions you might have, I do want to thank you, Presiding Commissioner McKissick, for your recognition of our field personnel, our plant personnel, and our system operators and our distribution control centers and our energy control centers. Those are the folks that this burden we're talking about falls on them all the time. They're the tip of the spear. They're the ones working 24/7 by 365. And it is encouraging to me to know that you and the commission understand that and appreciate that. So thank you for that recognition.
Well, that recognition was fitted, appropriate, and deserving. They do a great job.
Yes, sir.
And when we sat back and looked at the potential for rescheduling the technical conference back in January, we knew that had we moved forward and not reschedule it until today, some of those same people and the same that would be out there in the job that need to be doing work that you need to be working with might have been displaced.
Yes, sir.
And the highest and best use of the resources was right out there in the field, taking care of the challenging circumstances they face on an ongoing basis. So we appreciate the teamwork that they are engaged in, their readiness and capacity to do whatever's necessary to make sure that our system is functioning and operating, even when it's under unique strain and duress at a time where we could be facing a load shedding type of event. So we wanted to make sure we did recognize them.
Thank you for that.
Yeah.
I'll pass that on.
Sure, please do. And Mr. Holman, given your in-depth role in grid planning and integration, can you speak to how the proposed transmission and distribution investments support reliable system operations and how your team worked with Mr. Guyton's team and Mr. Fogg's team to identify the projects?
Yeah, yes, sir, Presiding Commissioner McKisson. That's a great question. Because I think it's real easy to get trapped in looking at this from a T, a D, and a G perspective. And sometimes you've got to organize that way. So I'm not saying it's necessarily wrong, but that's not the way the system responds. The system is an integrated system that interconnects in the real time, in the sub-second time frame between generation to transmission to distribution to customers. And now you're adding folks that are putting generation inside behind the meter. So what used to be radial fed distribution now needs to be networked, as Mr. Guyton spoke about earlier. So we have to, just like Duke Energy needs to be collaborating very closely with the commission because of all the changing parameters, that's even more effective within a company as big as Duke Energy, with our responsibility in the Carolinas, specifically here to North Carolina. We can't stick our head in the sand and say, all that I'm worried about is transmission, or all I'm worried about is distribution. And I think there was an exchange between Mr. Fogg and Mr. Guyton that talked about that. And so it operates as a system, and it is an unforgiving system because of the speed in which these electrons travel. So we have to, if we're going to live up to our obligation, the regulatory compact that we've spoken about before, we have to work closely together and not let organizations trick us, fool us into thinking we don't need to think in an integrated manner. And I think what we're going to be talking about over the course of the rest of the year, the integrated resource plan, Mr. Thompson mentioned it earlier, is a reflection of that integrated approach.
Thank you. And if you could you speak to how this new multi-value strategic transmission process is working at this time and how it will impact the type of transmission projects we'll see in future multi-year rate plans? I mean, we're tearing down the silos.
Yes, sir.
Getting everybody working collaboratively and looking at these projects in a very holistic way, but I don't know how it is changing and impacting what projects are being recommended and coming before us for consideration.
So I think the multi-value approach is the approach that gets us to a place where we can respond to the changes we're facing as fast as we're facing them as we move into the future. And I am not in that work group or in that space, so I can't speak with definitive experience, but I can tell you conceptually how I see it. We've got to look at things from the perspective of what's the most cost-effective, cost being an important word, effective being another really important word, a cost-effective solution. So the way this works is we're doing all these studies, whether it's our integrated resource plan team looking at the load out for 15 years, using 40 years of history, doing a regression analysis, attempting to determine how do you bound that? How do you bound that with a realistic view of what load might be, knowing that you're going to be wrong? That was kind of the inside joke in the control centers always. The one thing you know about a forecast, it's going to be wrong. Now, the question is, how much variability is in that wrongness? And so you're not going to be able to nail it, but bound it is an important key. And then you've got the customer growth component. I think somebody mentioned it for years. My recollection is the word was flat to declining load growth. And that's a tough place to be as a utility company, flat declining load growth. It's not what we're hearing now. You talk to utilities around the country, it's 2 to 3 to 4%. And so we can't ignore that. Now, will that last forever? I can't, I'm not Nostradamus. I can't predict that far in advance, but it's here now. I mean, if you look at what the loads we've saw over the last 3 peaking seasons where we've set some form of an all-time peak, people are moving to North Carolina. Businesses are moving to North Carolina. And they're not, I think as Mr. Guyton said, I think Mr. Fogg said too, it's not the big data centers you're hearing about. This is organic, traditional load growth. And so you can't ignore that. And so as you look at it from a multi-value perspective, you've got to figure out, okay, what are the constraints and validate them. We're using the Carolinas Transmission Collaborative to help us with that. But then the trick is, what are the available solutions to solve, to mitigate in a cost-effective manner those constraints and congestion you've just identified? And so the one way to do it is look at your traditional solutions, like what Mr. Fogg had talked about, transformers, conductors, breakers, but you also need to look at new technology, grid enhancing technology, static VAR compensators, StatComs, things like that. And you've got to look at all in the mix from a multi-value perspective and determine the cost-effective solution to that problem. And that's what this process that we've built around the DICES study, the cluster study, the validation with the Carolinas Transmission Collaborative, that allows us to explore solutions that we may not have considered. Now, at the end of the day, hope is not a plan, luck is not a plan. So you've got to lean into your operating experience. But I think this process will reveal to us the cost-effective solutions to the congestion and the constraints that we're seeing.
Thank you. I think I heard that same quote once before, perhaps when Winter Storm Elliott was being discussed.
Yes, sir.
Hope is not a plan.
Yes, sir. I think I remember that.
Yeah, you did, as I recall. Subject to check. Now, I guess the other question would be this. Has Duke done an analysis to see how the recent passage of Senate Bill 266 will impact the necessity for, say, the Red Zone 2.0 projects?
Yes, you're talking about the removal of midterm target.
That is correct.
Yeah, we do not believe that that'll have an impact on these red zone projects. The red zone projects are needed now. You saw how many generation resources depend on red zone 2.0. And I can say that with confidence because we're not looking out 15 years, we're looking out 2. And it's the strategy over the next 2 years of getting to where we need to be. There's no doubt transmission work, and Mr. Fogg can either correct me or agree, it's a long pole in the tent, right? Almost in every aspect, it's the longest thing you've got to get accomplished on the grid. And so we've got to find a way to be prudently proactive in the interest of our customers, in the interest of the Eastern Interconnection to get this stuff done. Because again, you start connecting generation without the appropriate infrastructure that it needs in transmission space, you're really experimenting with the grid. And that's, I mean, I've always found that to be very dangerous.
Thank you. Let me see if there are other questions from commissioners. Chair Brawley?
Mr. Holman, I always enjoy you. You and I have a similar haircut.
Yes, sir.
It's
very wind resistance, aerodynamic.
It is indeed. It's easier to comb in the morning.
Yes, sir.
Well, I've always said it's a gift from God because a bald-headed man knows life is not fair. And there's some things that you just man up and deal with
That's
because they're
exactly
not
right.
going to change. I wanted to ask, we listed there were 217 active generator interconnection requests dependent on our zone transmission projects. What's the breakdown of those generation types?
Okay, that's a great question. And I've got illustrations in my direct testimony on, I believe it's page 17 of both DEP and DEC. So it's broken down between solar storage, energy storage, gas, and nuclear upgrades.
Okay.
There's not, I don't want to make sure you don't walk away with, he's saying there's new nuclear, and there's not new nuclear, it's nuclear upgrades. And those are the assets that red zone and network upgrades will enable. And that's the breakdown. So it's really those 3 areas looking out the next 2 years. Now you go beyond that, and you'll hear more about this in the integrated resource plan that we've filed already. You know, there's some different things there that depend on technology, but we're talking about the next 2 years, generally gas, solar storage, and upgrades on our existing nuclear fleet.
Do you have numbers though on how
Yes,
much
sir.
is solar, how much is gas?
I do.
I'd like to put that on the record if you don't mind.
Just give me a second, turn my test on, and I'll share it for you.
And acting chair, while Mr. Holloman's looking for that, at the appropriate time, I've got a quick follow-up to an earlier commissioner question. I can provide a little more detail to Commissioner Gaeta.
Okay, very good. We'll recognize
Whatever.
you after this question.
So this is for DEC. And this is the RZEP. It's 575 megawatts of solar, 194 megawatts of battery energy storage, and 2,225 megawatts of gas.
Okay.
And there is another small amount, less than 100 for uprated nuclear. Then for DEP, it's 2,800 megawatts of solar, 939 of energy storage, 1,570 of gas, and 26 of nuclear uprates in DC. Excuse me, that was DP. That last set of numbers.
Correct, yeah.
Was DC.
And you said there'd been a lot of fallout in previous projects. How many potential projects were waiting on interconnection have dropped out, and what types?
So I do not have the specifics of that in terms of the numbers, but they were generally smaller projects. And what would happen in a serial sequential type study process, the burden of those upgrades would fall solely on that one project, and they just couldn't swing it until they drop out. The idea of clustering it and sharing those costs amongst the cluster seems to slow that down a little bit.
Okay. Thank you.
Yes, sir.
One quick question. I thought the nuclear uprates were up to 250 megawatts. Is that longer
I
term
think
though?
that's longer term, yes. sir.
Longer term?
Yeah.
Okay, all right. You wanted to go ahead and supplement.
Yeah, thank you. Commissioner Gaeta, before lunch, you asked a question, I believe, around ongoing O&M cost for our projects. And I indicated that was filed as part of our material. I'll tell you exactly where it is. So these exhibit numbers are the same for DEP and DEC. It's Technical Conference Exhibit 2 and Technical Conference Exhibit 3. And there's in both cases, the second column from the right is projected ongoing annual net O&M. And then the difference between Exhibit 2 and Exhibit 3, Exhibit 2 is at the area level, like Coastal 280 when I had that grouping of projects up there. And then TC Exhibit 3 is broken down all the way to the substation level. So for individual stations, you'll see those costs there. And the far right column is the installation O&M.
Okay, great. I appreciate that.
Thank you.
Now, let me see, are there any other commissioner questions before we move to the next panel? Commissioner Tucker?
Thank you, Mr. McKissick. Mr. Holman, always good to see you, sir. Your passion after 41 years is still there. It's recognizable, and I appreciate that.
15 minutes.
The map that you have with the red on it, since you were colorblind, is all down in the DEP area, primarily in South Carolina. Are all the RZEP projects, a lot of them with the interconnection that you discussed at length, because we have sporadic solar spread around that whole area down there, and you don't have a way, the generation from that solar, you need to, I think you mentioned issues such as you needed to study the generation over 15 to 30 years. You had to do the planning. You said NERC was required, but you didn't have to do these projects based on a NERC. You had to produce a study, right? Is that correct? And then you talked about congestion and generation reliability. And, I'm thinking there's lots of solar down there next to my hunting preserves, 1,000 acres of solar in the middle of Anson County, which is in the absolute middle of nowhere. And the transmission lines are incredible there, but somebody's got to hook up to those to get them to the place you want it to go and be able to redirect those electrons where they need to go. Is that a factor for the RZEP?
So
projects?
any generation interconnection's going to be analyzed for its effect on the transmission system, and congestion and constraints that appear need to be mitigated. And if you look at it from a cluster study, you've got to figure, okay, how do I allocate the cost? And we do it through a causation kind of methodology on a proportionality. That means whatever percentage of congestion that we believe a asset caused, they will get that same position, same portion of the cost. The way this works is the generator interconnector, and in the case of these assets here, it's Duke, but those assets pay for the required network upgrades. And so the system, if you look at generation that's already been connected, the network upgrades have allowed those generators to function reliably. And my evidence of that is that you're right, we have a lot of solar in the Carolinas. We are experienced solar operators. And I would offer this, as a person who sat through Winter Storm Elliott in the control center in Charlotte and watched our operators heroically deal with that, just the most difficult operating conditions I've seen in 41 years. Solar had its place. I mean, everybody knows it's not going to help you when it's dark outside, but it came on because it was a blue sky winter day once the sun came up, and that energy allowed us to recharge our pump storage. It was run hard across the peak. It allowed us to deal with some of the issues we were running into with the other generation resources. So as a former system operator, I'm agnostic to the technology. I just needed to provide me those essential reliability services I talked to you earlier about. The ability to ramp, the ability to be flexible, the ability to provide megawatts and megawatt hours and megavars. And I think we've just started to tap into the capabilities that these inverters provide to us as we go out into the future. But the pockets of red zones are, again, looking out over the next couple of years, the assets, the multiple interconnections that see these as constraints, the growth, the organic growth within our state of population, how are we going to serve those customers? And then these studies that we have to run for NERC to make sure we are resilient in terms of the loss of one facility, the loss of two facilities, the loss of three facilities. And I always describe that as security. The words have changed over the years, but my definition, simple mind as I have, is that security is pre-positioning the system to land reliably when something happens that you can't predict. You probably know it's a risk, but you can't predict when it happens. And so all of those studies point to these pockets or zones of congestion that we call the red zones. And then the projects address that congestion so that when the generation is connected, when that customer load gets to where it gets to over the next couple of years, we are positioned to handle it reliably. I hope I answered your question.
Well, kinda, but I'm just gonna say that consideration should have been given in the cost for the solar projects when they came online, that they were gonna have additional interconnection done through these RZEP projects because of the concentration of solar. That may or may not be correct, and you're welcome to dispute that. I mean, I just see it in a specific area there, and I look at it, and of course, Winter Storm Elliott was very, very difficult, especially for you because Duke had never had a blackout because for 80, 90 years, they'd used coal as a fixed asset and nuclear to provide power. But with the growth that we have, I'll move on from there. You used an example of your town and the growth in your town and the roads not keeping up. Why are the roads not being kept up?
Yes, is as good.
I'll tell you why. I was a senator for 8 years. DOT doesn't have the money. And then you put Helene on top of it. But my point is they don't fix your road because they don't have the money. When did we get to a point where we can't you build everything to a maximum? You can't keep your head in the sand. You've got to be on top of it. All of your passion's there and it's real. And I understand building the maximum, but when do we get to a point when the customer can't afford it anymore? Just simply cannot, because you're talking about spending billions of dollars, getting a return on equity, and then the customer's got to pay for all these projects for the interconnection that we need to do that. If you did not have the RZEP, would we have lost power? I think your answer would probably be yes, but if we didn't build that, we just have a bunch of solar sticking out there. We could throw a gas plant and fill in the blanks right there and move on from there. So the RZEP project is costing a ton of money added to the rate base, and that road, you're going to build it, whether you got the money, the customer's got the money or not, you're gonna go ahead and build it, and they have little or no choice in the matter. And you could have not done that or not done it as soon as you did it to spend the money to get the ROE. But I really believe that you were doing it because you thought the integrity of the system was online. And that's why in your VP role, you push forward with the RZEP projects. I just don't know where we get down to the squeeze of what Duke says we need and the growth that we have and all those things. Could this not have been money spent somewhere else or not spent so the rates don't have to go up? That's just where I'm coming from, sir.
And I can appreciate your concern. I think that's kind of y'all's job to express that. concern.
That's right. But we still give you a nice, healthy ROE, which you know was just established here about a month ago on how well Duke did with their ROE. And I'm just saying that we're going to go right back in with another rate case right now on the docket. We're going to move forward with that with another increase and another increase. And we can pay for RZEP, we can pay for another CT, we can put in more solar over here, we can do this. At some point, we got to start thinking a little bit out of the box on how we utilize what we have and use that generation that's there. And you know, I've mentioned 2 or 3 times about coal. They're paid for assets. And, you know, I realize the Obama-Biden administration directed Duke to shut them down, and Duke will not shut them down until they have something to replace it, which is absolute common sense. And I appreciate that. But the opportunity, we got to get somewhere, because you don't go to the public hearings, I guess we go to. You don't hear about what we hear about, and then we approve your increase. The responsibility's on us to do that, and we're the ones that catch it. Of course, the folks that do catch it and public staff does too. But I mean, this is all wonderful what we're talking about. And I stated earlier, I was against the red zone projects to begin with, because I didn't think they were virtually needed as badly as you say they need to be. And I don't doubt you're not right, sir. I would like to build out anything you wanted to have, but I'm telling you, it's getting to be a squeeze here, whereas, you know, the power bill is getting to be a car payment size or a mortgage payment size. And we got to start thinking inside the box a little bit about those folks that sit outside the box and watch what we do. So, you know, DOT doesn't fix your road because they don't have the money. And we're going to get to a point where we can't just keep on giving rate increases because we need to do this. We need to do with what we have to a certain extent, and we're not utilizing it. We really need to do a deep dive and take a look at where Duke's going. I don't believe because you're a monopoly, you're the enemy. I do not believe that. I know that Duke Power has served us well and is in the top 3 in the U.S. on KW rates at 13.9%, 9 cents a KW. Y'all have done a great job, but I'm just telling you, it is, I sit here and look at the transmission, I look at the distribution, and I look at the $5 or $6 billion added on to that, plus the CTs, plus everything coming down the line. Something's got to give somewhere, gentlemen, and that's all I got to say about the matter. But I appreciate you and your 41 years. I want you to know that. And I know you're probably right. But I'm just saying we need to reflect and look and think, you know, inside the box a little bit about what's happening outside. Thank you, sir. Thank you, Chair,
Yes,
Commissioner
go ahead.
McKissy.
Yes, so I appreciate your comments. And when you talk about affordability, I couldn't agree with you more. And I can just tell you from the company's perspective, we focus on affordability every day. Just personally, I've got 3 daughters, their husbands, and 7 grandkids that have to deal with their power bill. So I hear it from them. I know it's not the avenues that you hear it in, but we fully realize we don't have a blank check in this. I mean, I can promise you that. We're trying to figure out the cost-effective way to get us from here to there. And part of the story of the red zone was we could delay those and have them be network upgrades, but would never meet the timing requirements. We would be experimenting with the grid. We would be sitting there with the generation asset all ready to go. You know, we talk about Mr. Thompson's solar projects, and we can't count them as designated network resources or capacity. And we continue to have the growth we're seeing in our population. You end up in a very bad spot. And what we're trying to do, and I know maybe it's trying to thread a really difficult needle, we're looking for those cost-effective ways to deliver cost-effective reliability to our customers. And some of those customers, my 7 grandkids, and I kind of care about them a little bit. So I appreciate your challenge. I take no offense to being challenged. We're in this same game together. We don't do anything without your oversight and instruction. And we've got to figure this out, don't we, Commissioner Tugger?
Thank you, sir.
All right. Thank you for those comments. Commissioner Guida, you have a question? Go right ahead, sir. And then we're going to take a quick break.
Thank you, Commissioner. Mr. Holman, you may have already answered this, but bear with me. Is it accurate to state that the RZEP and network upgrades you presented here are an element or perhaps a key element of the current filed IRP action plan? When I think about short-term action plan?
Yes.
Okay.
Yes, sir, they are. I mean,
Okay.
they enable it. They enable it.
Okay, very good. Thank you, Commissioner.
Thank you. And I think Mr. Holman stated earlier, hope is not a plan, but what we have before us for our respectful consideration as we move forward in this rate case is. So we will have a chance to have them come back during the context of the rate case and provide testimony on these relevant subcomponents at that particular point in time. Today is just a technical conference, so thank you, Mr. Holman, for your testimony. We're going to take a 5-minute break. So it's now 3:43. Why don't we say we come back about 3:47 and we will conclude our work at that time. We'll then move on to reliability microgrid project. Okay? Thank you. There he is. Okay. Very good. All right, we're gonna go ahead and continue with the final segment of this technical conference, and we'll now move into the topic of reliability microgrid project. Mr. Thompson?
Thank you for writing, Commissioner McKissick. I'm Gray Thompson, and I'm the Director of Energy Storage for Duke Energy's Carolinas service territories. In this role, I originate and develop battery projects in our Carolinas territory. I also oversee, well, I'm involved with the procurement of major equipment and seek internal approval and funding for our battery investments. And despite being relegated to the junior varsity table, I'm very privileged to present you today the energy storage project that's proposed as part of our second multi-year rate plan filing. And the others did not do this. I'm going to give you a time estimate. I'm going to go about 12 to 15 minutes, first discussing grid uses of energy storage, then turning our attention to the program description and cost, and finally summarizing both the quantified and qualified benefits to North Carolina customers of my MYRP2 project. Next one, please. There we go. Batteries are ubiquitous in modern life, and everyone in this room is generally aware how they're used to enable handheld electronics and electrified transportation. But to a growing extent, battery energy storage is providing utility grid operators a flexible tool to serve a variety of beneficial purposes. And the flexibility of large battery systems, I love analogies. It's like a Swiss Army knife. You can use it for different things, but not necessarily at the same time. So let's explore that. The graph Duke's created here on the left side of the slide illustrates the named services which grid-connected storage resources can provide. And note that the location on the grid where the storage resource is located can dictate which service it can provide. So in the interior of the graph, we distinguish the potential benefits of batteries sited behind a customer's meter, interconnected to the transmission system, interconnected to the distribution system, or sited at a generator. And then the exterior of the circle demonstrates the functions that different siting strategies can support. A main takeaway of the chart here is the number and variety of purposes that energy storage can serve based on configuration, nearly always including the benefit of discharging to meet customer energy needs during peak hours of electric demand. But one of the lesser known utility purposes of energy storage resources is that the use of a battery to improve reliability to a limited and targeted number of customers served by the distribution system. Such batteries can serve as a cost-effective alternative to and deferral of traditional wires investments. Now, today's distribution and transmission technical conference is intended to explore T&D investments, and therefore I'll focus on a battery project type which will provide benefits to the distribution grid. A project type we'll refer to as reliability microgrids. Before I leave this chart, though, I want to strike home the idea that Duke Energy's reliability microgrids are optimized to improve reliability of service to some targeted distribution customers, but most of the year, the battery associated with our project will provide benefits to the system analogous to a generator by helping meet total system need, discharging during hours of peak demand. Next slide, please. So let's talk a little more about the battery microgrid type and what's being proposed as a part of this multi-year rate plan. Multiple battery microgrid projects were explored and approved in our initial multi-year rate plan. But our current filing proposes a single project of this type known as the Williamsboro project. To fully understand the Williamsboro project, you first have to understand Duke Energy Progress's service to customers in a very specific portion of the distribution system. Now, the image in the center of this slide shows the topology of the Williamsboro circuit. As you can see, a geographic feature, in this case, Kerr Lake, and service territory assignment boundaries have resulted in some of our Carolinas customers being served by a long, radially fed circuit. Now, a notable unique feature of this situation here, you'll notice the line across the top of the map. That's the North Carolina-Virginia border, making this the literal edge of Duke Energy's service territory and the North Carolina distribution system. So these geographic and political boundaries have produced a cluster of customers served by that long, radially fed distribution voltage circuit. And the significant linear distances create exposure to outage causes like public interference, car impacts, and wildlife and vegetation. And then the inability to connect to other power sources means that traditional options for reliability improvements, like an alternate backup feeder explored by Mr. Guyton in the self-optimizing grid solution earlier in the day, those aren't available here. And all these factors have combined to result in some of the customers here in the graph experiencing a relatively higher outage frequency and duration than many others. So to improve reliability, companies proposing to build a microgrid based around a single large battery, which will be sited adjacent to the targeted customers. With a utility scale battery and the related interconnection equipment, if there's a loss of utility service, the battery will form a microgrid area and serve the customer's electrical meters until repairs are made to the normal service. Essentially, when called upon, automated devices are going to disconnect the end of a circuit from the larger distribution system for a period of time. And then the islanded section of the circuit and the customers served by it will then be restored to service with energy coming from the battery asset. Now, while the battery's powering the customers in the microgrid, crews will be working to make repairs to the distribution system so the customers can be transferred back to their normal method of service prior to the battery being exhausted. Continuity of electric service to this portion of the system isn't inconsequential. Contained amongst the approximately 1,000 customers in this section of the grid are those who provide basic and safety-related services like churches, volunteer fire departments, streetlights, TV broadcasting stations, cell towers, restaurants, U.S. Postal Service, grocery and gas sales. During conceptual engineering, the battery project was optimized to economically mitigate a significant number, more than 90%, of the outages that the area has historically experienced over the past few years. Now, remember, when not in use for reliability, the battery that's at the heart of the microgrid, Williamsboro microgrid, will dispatch to provide services such as capacity, energy arbitrage to meet the growing demands of legacy and new customers all across the DEP system. Williamsboro microgrid is a prime example of how tech advancement can benefit utility customers, and it gives distribution planners a tool to solve a grid issue which previously did not have a viable solution. Last slide, please. All right, having looked at the context and the proposed solution, let's focus on the different benefits. So as with the projects discussed by Mr. Guyton, Mr. Fogg, Mr. Hallman, the proposed microgrid investment will result in both quantified and qualified benefits. First, using the battery energy storage tech in a distribution microgrid helps to avoid direct costs of outages to customers. Helps them avoid costs associated with nuisance events like spoiled food, blown fuses, as well as more important items like lost business hours for work from home customers. The rapid restoration of service also ensures continuity of business and normal pattern of life activity for many hours of the year when it would otherwise stop. And some of the positive effects of this include the continuity of public safety assets and other critical infrastructure available when it would otherwise not be. And then finally, the last qualified benefit here, continuing a disciplined and limited deployment of the reliability microgrid solution builds confidence in microgrid's development and construction and operation so it may reliably be used in planning and thereby available as a non-wires alternative, deferring investment in traditional solutions that may have been otherwise utilized to increase reliability. So the Commission and audience may be aware of Duke Energy's efforts to improve service to customers in Hot Springs, North Carolina, which entailed construction of a microgrid centered around a solar plus storage system. Not only has that project allowed for more efficient operations of the wider Duke Energy Progress system, but it restored service to hundreds of customers following Hurricane Helene, several days faster than would have otherwise been possible. Construction of Williamsboro microgrid project will continue to ingrain and improve upon the first deployments of microgrids to ensure that they are available to system planners as they assess ways to improve upon our safe and reliable delivery of electric service to customers, which they count upon. And then in addition to these three categories of qualified benefits, Williamsboro project will accrue millions of dollars of benefits to Duke Energy Progress customers through two main streams. First, asset will be charged and discharged in a way that will avoid the purchase of electricity during high-priced periods and/or partially defer the need for construction of dispatchable generation for the next 3 decades. Additionally, the microgrid will improve the reliability of service to several hundred customers in lieu of a significant poles and wires improvement effort. And then together, these two streams are valued at approximately $21 million over the lifetime of the asset, compared to approximately $17 million for the cost, leading to a benefit cost ratio exceeding 1. Now, one note on the cost benefit analysis. The assumed cost modeled here, they account for Duke Energy's efforts to ensure that the upfront costs are offset by significant federal investment tax credit, initially made possible by the Inflation Reduction Act, but then confirmed for the next many years by last summer's One Big Beautiful Bill legislation. The presented CBA incorporates a 50% investment tax credit, including a 30% base credit, a 10% adder for being excited in an energy community, and a 10% adder for purchasing equipment, which contains domestically sourced material. So in essence, this work will accrue millions of dollars in benefits and federal dollars to Duke Energy customers as these benefits are passed on through rates. So I promised you 15 minutes, but it's quite a bit of material, including the use cases, a summary of the project, and most importantly, customer benefits. I'm privileged to be here representing the project and happy to answer questions.
Thank you, Mr. Thompson. Let me pose this one question to you, and it relates to what the commission stated in the last multi-year rate plan proceeding. And in that proceeding, the commission stated in its conclusion as it related to microgrid projects, and I'm going to quote you the following. The commission notes that concerns and recommendations raised by witness Thomas, based on his analysis regarding the higher cost of microgrids over grid scale storage and microgrid cost allocation, merit consideration in future rate cases. The commission also notes witness Thompson's recommendation that the DEC consider adding additional battery storage capacity at the Allen site and DEC's willingness to explore a second project at the Allen site if there is land available at the site. Further, in future rate cases, the commission directs DEC to present detailed evidence demonstrating the completed multi-year rate plan microgrids and how they have provided production plant services before allocating new microgrid costs to those production and distribution categories. Finally, the commission directs DEC to investigate increased storage capacity at the Allen site and to report on its findings in this next general rate case proceeding. Can you point to me to where in the T&D filings or in the testimony the commission can find information responsive to that request?
When they draft the question, it's a lot longer than they think can be said. But what 4 parts I got from it were scrutiny of production benefits, investigation of continued investment at the Allen 2 site, and And then it came back again to evidence of production benefits.
That is
If I-
correct. I think that's a pretty good summarization.
Thank you, sir.
But, and that came from a specific quote, and
Yeah.
I stuck with the quote as carefully as possible.
Thank you. First, I am very familiar with that passage. I believe it might have been specifically called out in a settlement agreement filed prior to commission order. So I'm very well aware of the gist of us doing all those things. So first, from production benefits, able to successfully point to Hot Springs. Hot Springs is a good example of a end-of-line battery installation, and show me that it is producing benefit. As a part of the Certificate of Public Convenience and Necessity, I want to avoid the acronym, the company was required to file annual operational reports before the commission, and which we have done. And so in public record, there is available that the Hot Springs system, microgrid system, on a daily blue sky basis is returning energy to customers at the time of most need, at the time of high demand and most need. So we believe it's responsive to show that benefits have been produced from microgrids to have been satisfied by our continuing annual report there, but are obviously willing to explore that more through discovery in the multi-year rate plan docket as appropriate. Second part was the investigation of additional investment at the Allen site. And while that is not in scope of T&D, I'm happy to address it. The Allen batteries are intended to serve most analogous to production, most analogous to generation, not as a investment in lieu of poles and wires solution. Happy to report that there continues to be investment at the Allen site. There are two major phases of investment there, which we filed as a part of the Duke Energy Carolinas multi-year 2.0 system or filing. So, you know, they are not providing T&D. They are not intended as T&D investments, but we have been responsive to both of those items from the quote that you read, Presiding Commissioner.
All right, thank you. Let me see if there are any further questions from commissioners. Chair Brawley, Commissioner Tucker. Commissioner Gaida, go right ahead.
Okay, thank you, Chair. Do you have an evaluation process in place to address similar edge of territory situations like you saw there in Williamsboro?
The bringing Williamsboro, so I'll first say that characterize our here as limited and as disciplined. We are carefully evaluating situations and have in the past said this might be an opportunity to move a project forward and then for one reason or another stopped. There are numerous projects in essence that didn't come to today's technical conference. So I think that's the basic answer to your question, Commissioner Gaida, is, you know, is there a place to look at others? Yes, there is, and we have done it.
Okay, great. Just a little follow-up. I guess specific to this project, or I guess it would apply to the other ones that you looked at as potentials. Was the and you may have said this, but was the ICE calculator a significant part of the benefit side of this equation when you were doing the cost benefit?
The short answer is no.
Okay.
And I'm happy to differentiate between the reliance upon and the use of the ICE calculator in the other projects proposed as a part of today's technical conference and the microgrid. It boils down most concisely to number of customers served. The number of customers served by the equipment to be improved upon by the multiple billions of dollars of distribution and transmission investments pales in comparison to the much more limited scope of this project, where there is a larger system benefit, but in terms of reliability improvement, which is the focus of the ICE calculator, there's 1,000 customers. And the relative size of the data set, we think, bears out a different sort of analysis. And for that reason, ICE calculator dollars were not incorporated into the cost benefit ratio shown on slide 61.
Oh, okay. So then, but, and maybe without having to get in a lot of details, but the reliability impact here for those customers, is that still factored into the benefit side then? It's
Yes,
just
sir.
not specifically using the ICE calculator?
That's correct.
Okay. Okay.
Happy to elaborate.
Okay. I guess my only question would be, is in that number, can you characterize what portion of that benefits number is the reliability element versus the other system benefits you just spoke of?
It's about half and half. That was not by design. That is not our, we don't look for projects that are half and half. But we value both the production efficiencies and deferred investments in other capacity resources, as well as the deferred cost of an analogous reliability poles and wires solution. And in this case, they were about half and half and exceeded net present value of total costs.
Okay. Okay. Thank you. That's all I've got.
Commissioner Tucker.
Yes, thank you, Mr. Thompson. I appreciate you carrying up the backside of the JV.
That's for last.
Seat there. Help me understand a couple of things. As you share with me, there's no microgrid in Williamsboro now.
No, sir.
Okay, but there is lines and poles serving customers, right?
Yes, sir.
And so does Williamsboro it have more outages than the regular system, any more than the regular system?
Yes, sir.
And the reason for that is?
There are limited improvement options, and it is a long and exposed radial line. Many of the customers of our system are able to have been improved over the years through alternative feeds, alternative sources of power, so that if the line that normally serves your house is faulted on any given day, the length of your interruption might be minimized, mitigated by rerouting of power. In this particular instance, that is not possible. There might be some more limited improvements that can be made, but nothing substantial enough to accomplish huge and significant improvements of reliability that would be realized if you were able to get an alternate source of power. That's the heart of the self-optimizing grid investment type Mr. Guyton was talking about at the start of the day, which is itself the backbone of the distribution programs. That is not possible here due to the geography.
Okay, so the motivation for the microgrid is to provide reliability and limit the outages for this group of roughly 1,000 customers.
That is the primary driver. Yes, sir.
And we're going to invest, if my math's correct, 1,700 per customer
I haven't
in trying to provide this upgraded, lesser outage, more reliability microgrid. Is that what I'm looking at?
the benefits that will result will be improved service. That was the original intent of the origination of the project. It will also provide significant benefit to all Duke Energy Progress customers as it acts analogous to a generator, providing a source of power to the entire system on a daily basis, which results in real measurable dollars and benefit to all customers.
So you don't pull that power down unless these 1,000 customers may need it? Is that what I'm just trying to understand?
Yes, sir. The system will not act as a microgrid on a daily basis. It will act as a microgrid sometimes during the year. It will act as a microgrid in those times when these customers have been experiencing outages, which is not every day, but sometimes during the year, and at a rate that is higher than the system average. It will act in a microgrid in those situations the rest of the year. It will act, the battery will be producing real benefits analogous to a generator. That might respond to your question.
Yeah.
sir.
Tell me what the option was, poles and lines and upgrades. What was that number like? I know you're going to be 30 million, but go ahead and tell me.
As I was describing to Commissioner Guida, it was about half and half. You can see that our benefit cost ratio is slightly above 1, benefits slightly exceeding the cost. And I think I've referenced in my comments, $21 million, roughly half and half. And it holds, this simple math holds true. The alternative investment that we were able to provide a cost estimate for was roughly $9 or $10 million, somewhere in there. That is not a high reliability, high confidence solution that could be, you couldn't tell me today, Mr. Thompson, go build that and tell me that you can 100% do it. It would be a multi-mile new line construction through service territory that Duke Energy does not serve. And so I would not be able to sit here and say, yes, we could build it, but it is a reference cost for the construction of the cost benefit analysis and something that can be compared to.
You mentioned something about geography. Is that mountainous there?
Not mountainous, no.
I didn't think so.
No, Hot Springs was mountainous.
Is this one of
Tucker.
these projects we could not do and save the ratepayers $9 million or $11 million and not do this and put in poles and lines?
Believe that there's continuous customer expectation that we realize the benefits that were described. In this particular instance, it is an alternative to a reliability improvement, poles and wires reliability improvement. It continues to, doing this project continues to ingrain and improve upon our ability to do microgrids, our ability to construct this if and when situations arise where we want to build a microgrid here or in the future. And then finally, we've shown that it produces real benefits that exceed its cost. So for those reasons, we feel it's prudent for to present here as a part of our multi-year rate plan for the consideration of the commission.
Well, you certainly can present it. Thank you.
Thank you, Commissioner.
Just one quick follow-up. As I recall, Williamsboro, it's going to be on the North Carolina side of that North Carolina-Virginia line.
Yes, sir.
Near Kerr Lake, right there between Vance and Granville counties. Is that right?
Forgive my lack of geography, but the rest of it was right until the county names.
Okay, until the county names.
Yes.
So is it in Vance or is it over in Granville? Or you just don't recall?
I wouldn't want to.
That's fine.
Yes, Commissioner.
Yeah, because I'm kind of surmising that geographic area myself.
Thank you.
Okay. Thank you. Well, if there are no other commissioner questions, I know we want to recognize Duke for final comments for today. Oh, okay, Chair Brawley.
Every time batteries are discussed, I hear batteries have a 4-hour life. And I wondered, it sounds like you're depending on batteries providing power for more than 4 hours. Is this that you're dispatching at a much lower rate than the rated? Or just tell me how that would work.
Thank you. The first part of the question, let me confirm, our standard duration for our large batteries, which are dependent upon to meet the needs of the resource plan. For those assets, 100 megawatts size, large batteries, 4 hours is our standard duration. In this case, the size of the battery was optimized to get more than 90% of the historic outages experienced here. So the duration at most load situations is sized not to go on 4 days worth of outage, but that duration which would get more than 90% of the historic outages. So in that sense, if the outage goes on 4 days, this would not be sized to get it. But it's a disciplined and economic investment to get a significant portion of the outages which have been experienced here without over-investing.
Is that 4 hours?
I think the duration, let me give you an answer that's subject to the check. I think the duration that we targeted was somewhere in the 4 to 6 hour-ish range. I'll have to come back with a more precise answer, but it was less than 1 day.
Okay, thank you.
Yes, sir.
Are there any other commissioner questions? If not, let me thank all 4 panelists for being here today and for answering to the best of your ability and capacity the questions that we posed. I think you've done an excellent job. You provided us a great deal of context and insight, and I think our commission staff got the vast majority of their questions asked and answered as well. On that note, I'm going to look to Duke now for final comments for today.
Nothing else, Commissioner McKissick. We have a few supplementals for you, and we'll make sure to get that information over to you.
Excellent. We'll look forward to receiving those supplemental responses. On that note, we hereby stand adjourned. Thank you for being here.
Thank
Have a
you.
great day.